Picture a modern city at night. Glass towers glowing, traffic humming, screens painting the darkness with color. Now, let it all dissolve. The lights fade, the roads melt away, the concrete peels back. In a heartbeat, the noise of engines is replaced by the roar of wind and the distant crack of thunder over an ancient floodplain where no human has ever stood. Before history had a name, before our species existed, the Earth belonged to giants. Not just big animals, but colossal dynasties that ruled for 165 million years. Our entire recorded history fits into the last tiny sliver of that span. A brief flicker compared to an era when dinosaurs were not curiosities in museums, but the everyday rulers of a living, breathing world. We step back hundreds of millions of years into a late Jurassic Valley. Dawn mist clings to the ground. The air is heavy, humid, thick with the green scent of ferns and the dust of drifting spores. Far off, a volcano paints the horizon with a dull red glow, its plume turning the sky the color of cooled ash. Then, beneath our feet, the ground begins to tremble. A herd of sauropods moves through the floodplain, each one longer than a line of city buses. Necks arc higher than apartment buildings, sweeping slowly over the canopy, like living cranes. Hearts the size of small cars push blood uphill with every beat. Their footsteps land with the deep, rolling thunder of distant artillery, echoing off sandstone cliffs and sending ripples through pools where dragonflies as wide as your hand lift into the steaming air. This is a world of scale we can barely imagine. Tails swing behind these giants like collapsing construction booms, flattening shrubs and carving furrows in the mud. The ground is a maze of footprints large enough to cradle a human body. Overhead, pterosaurs ride warm-up drafts like gliders, while early birds flicker between the branches. Even the plants seem oversized, with tree ferns and conifers rising in layered walls of green. How did bodies this massive breathe, grow, and move without collapsing under their own weight? What kind of planet could feed a valley full of the biggest creatures to ever walk the Earth, day after day for millions of years? And how could a dynasty that endured for so long vanish in what, on geological timescales, amounts to an instant? To answer those questions, we have to go back to the beginning, to the shattered world after the greatest extinction Earth has ever seen. Join us as we follow evolution from small experimental reptiles in the Triassic, through the Jurassic Golden Age of long-necked titans, into the Cretaceous arms races of armor, horns, and megapredators. Using fossils as time machines, we will set the stage for understanding not only how these giants lived, but why their age finally ended. To understand this age of giants, we first have to be precise. What exactly is a dinosaur? Not every ancient reptile with teeth and claws qualifies. Pterosaurs soaring overhead and mosasaurs prowling the seas were close relatives, but they were not dinosaurs. Dinosaurs were a distinct group of land-dwelling reptiles with an upright stance, their legs tucked beneath their bodies like living pillars, supporting frames that would one day produce the biggest creatures to ever walk the Earth. Once we know who counts, the next question is where and when. The Mesozoic era was not one continuous uniform dinosaur time. It was a 165 million year saga split into three very different acts. In the Triassic period, we meet small, agile forms like Chelophysis, darting across the hot, dry supercontinent of Pangaea. In the Jurassic, warm, humid climates and rifting continents set the stage for colossal sauropods and the first true birds. By the Cretaceous, the world is broken into separate landmasses. Shallow seas, flood continents, flowering plants spread, and regional dinosaur worlds begin to diverge. So what did those worlds actually look and feel like? If we could step back hundreds of millions of years, the air might seem thicker, richer in carbon dioxide, the forests dominated by conifers, cycads, and giant ferns taller than houses. Some periods had no polar ice at all. Others saw seasonal chills even near the poles, where dinosaurs still roamed. We want to know how these shifting climates, rising seas, and drifting continents shaped dinosaur evolution, behavior, and ultimately their extinction. Then there is the question of size. How did some dinosaurs grow so massive, with necks longer than city buses and bodies heavier than a convoy of trucks, yet hatch from eggs smaller than a soccer ball? How did their bones, lungs, and hearts cope with such scale? And why did gigantism flourish in some periods and places, but not in others? Join us as we follow the clues hidden in bone texture, growth rings, and even fossilized footprints to explore a world of scale we can barely imagine. To answer any of this, we rely on detectives of deep time. Paleontologists work in deserts, quarries, and polar badlands, cutting through rock layers like pages in Earth's history book. A red sandstone bed might record a Triassic floodplain. A gray shale above it might capture a Jurassic lake. Each layer locks in different creatures, climates, and catastrophes, letting us watch the Mesozoic change one slice at a time. Yet our knowledge is still fragmentary. Many of the largest dinosaurs, like Argentinosaurus, are known from only a handful of bones. New finds can overturn record books overnight. A single thigh bone, a new trackway, even a feather trapped in amber can force us to redraw behavior, appearance, or size estimates. In this film, we will move period by period through the Triassic, Jurassic, and Cretaceous, then dive into how gigantism worked, how we know what we know, and finally, how an asteroid and a changing planet ended their reign but left birds as living heirs of this ancient dynasty. For the next while, think of this not as a video playing in the background, but as an evening we spend time traveling together. Not just watching, but walking, flying, and wading through 165 million years of deep time. Where are you right now as we step back hundreds of millions of years? Tell us in the comments which country or region you are watching from and what time it is where you are. Share which dinosaur or which period, Triassic, Jurassic, or Cretaceous, you are most excited to visit. Your answers will turn this from a solitary screen into a global group of travelers, all crossing the same ancient world at once. Join us as we settle into a different rhythm than a short clip or a quick highlight reel. This journey will begin with a cinematic buildup, lingering on empty coastlines and silent conifer forests before the first small, two-legged proto-dinosaurs dart into view. From there, the pace will become a steady, explanatory flow, carrying us from fragile Triassic survivors to colossal Jurassic sauropods, and finally, to the crowded, diverse ecosystems of the Cretaceous, just before extinction slams the door. We will cross supercontinents as they tear apart, watching Pangaea split into separate landmasses and shallow seas flood the interiors of continents. We will see oceans rise and retreat, climates shift from parched interiors to warm, humid coasts, and forests transform from fern-dominated undergrowth and towering conifers into landscapes threaded with the first flowering plants. At each step, we will ask, how did dinosaur bodies respond to this changing Earth? Not just in size, but in design. Necks will lengthen to sweep over entire groves of vegetation. Limbs will thicken into living pillars to carry weights that rival modern jetliners. Feathers will appear first as insulation and display, then as the flight surfaces that allow some descendants to survive when the age of giants ends. Along the way, we will meet creatures longer than planes, including sauropods, whose bodies could rival a Boeing 737 in length, yet began life inside eggs smaller than a soccer ball. We will stand beside predators with bone-crushing bites, their skulls engineered to drive teeth through armor and bone. And we will follow feathered hunters, no bigger than a turkey, darting through undergrowth, outliving their massive relatives, and inheriting the skies as the only dinosaurs to see the modern era. One question before we begin in earnest. When you imagine the biggest creatures to ever walk the earth, do you see only towering monsters? Or can you picture the fragile hatchlings, the shifting continents, the rising seas that set the stage for their evolution? Hold that image. In the next section, we return to a devastated planet after the Permian extinction and watch the very first dinosaurs emerge. The image of fragile hatchlings and shifting seas hangs in your mind as the sound around us softens, then falls away. The screen fades to black. For a heartbeat, there is nothing. Then a low swell of orchestral music rises, deep and atmospheric, like distant thunder rolling over an empty ocean. Out of the darkness, Earth appears in the void of space, a blue and white sphere slowly turning beneath us. We step back hundreds of millions of years in a single cut. No cities, no ice caps, just clouds, water, and an almost unbroken sweep of land. The camera glides closer. That land is Pangaea, a colossal supercontinent stretched from pole to pole. Its deserts burned red, its coasts fringed with shallow green seas. This is the stage on which the first dinosaurs will appear. But right now, it is only rock and possibility. The music climbs, adding strings and distant choral voices, as if the planet itself is taking a breath. Across the center of the frame, a title slowly materializes in stark, bright letters: The Entire Age of Dinosaurs. Beneath it, a subtitle fades in, precise and understated: 165 million years of prehistoric Earth. We hold on this image, letting you feel the weight of that span. Humans have studied dinosaurs seriously for barely 2 centuries. Dinosaurs ruled this ancient world for a length of time that makes our entire history look like a flicker. The narration falls silent. Only the music remains. We watch as Pangaea begins to change. Faint, glowing lines trace along weaknesses in the crust, then widen into newborn oceans. The supercontinent subtly stretches, cracks, and drifts. In slow motion, familiar shapes hint at the continents we know today, peeling away from one another like pieces of a vast geological puzzle. Each shift in the land hints at a new chapter. As seas flood low-lying interiors, we glimpse where future shallow oceans will nurture reefs and marine reptiles. As landmasses separate, we sense how isolation will set the stage for different dinosaur lineages to rise, specialize, and sometimes vanish in extinction. Without a word, we see how the movement of plates will guide evolution itself. The music swells to a peak as the camera begins to descend. The title and dates fade, leaving only the spinning Earth. We plunge through the clouds, racing toward a dry, rust-colored coastline on the edge of Pangaea. The air grows hazy. Volcanoes smolder on the horizon. Sparse conifer forests and strange, low ferns pattern the ground below. We slow above a Triassic landscape, quiet but expectant. No colossal sauropods yet, no famous predators. Just a harsh, recovering world, waiting for its first true giants. The music narrows to a tense, held note as we drift lower, toward the shadow of a small, agile reptile darting between the trees. Here, at the dawn of the Mesozoic era, the story is ready to begin. The dawn of the Mesozoic era does not open on peace. It opens on ruins. Before these small Triassic reptiles ever dart between the trees, Earth has just survived the greatest biological crisis in its entire history. We step back hundreds of millions of years to the end of the Permian period. Almost everything is alive. Then almost nothing is. In a geologic instant, up to 90 to 95% of marine species vanish. Around 70% of land vertebrates disappear. Coral reefs collapse. Forests thin and die. This is the Permian-Triassic mass extinction, and it nearly ends complex life story on land. What could scar a whole planet so deeply? Evidence points to colossal eruptions in what is now Siberia, known as the Siberian Traps. For hundreds of thousands of years, vast sheets of lava pour out, releasing massive volumes of carbon dioxide and other gases. The atmosphere warms. The oceans absorb heat and CO2, turning more acidic. Oxygen levels in the seas plummet, creating anoxic, suffocating waters where few creatures can survive. On land, climate swings become brutal. Some regions bake under intense greenhouse conditions. Others suffer from drought and wildfires. Acid rain may have fallen. It is a hostile, unstable world. A world of scale we can barely imagine in its devastation. When ecosystems are stressed this hard, food webs snap. Top predators starve. Delicate specialists vanish. Only the hardiest generalists endure. Yet this same catastrophe quietly resets the game. When so many species disappear, they leave behind empty ecological space, vacant predator roles in rivers and coastal plains, abandoned herbivore niches in forests and floodplains, whole habitats with almost no large animals at all. Extinction erases, but it also clears room for evolution to redraw the map. Into this ecological void step several groups of reptiles, each experimenting with new body plans and lifestyles. Among them are the early archosaurs, the broader clan that will eventually include crocodiles, pterosaurs, and dinosaurs. At first, they are just one set of survivors among many, modest in size, lightly built, running on more upright limbs that let them move quickly and breathe efficiently. Join us as we watch this recovering world sort itself out. For millions of years after the crisis, archosaurs compete with mammal-like reptiles and other survivors for those open niches. Will the agile, fast-breathing archosaurs dominate the coasts and floodplains? Will other lineages reclaim the role of the biggest creatures to ever walk the earth? At this stage, nothing is guaranteed. This is the deeper context for the Age of Dinosaurs. It is not simply a parade of giants, but a long, fragile rebound from near-total collapse as life tests new designs, succeeds in some directions, and fails in others. In the next chapter, we will see how a few of these early archosaurs cross an invisible threshold and become the first true dinosaurs, setting the stage for their rise from obscurity to planetary dominance. To follow these early archosaurs across that invisible threshold, we first need to know what they became. What is a dinosaur, really? In a world filled with massive reptiles, strange wings, and sea dragons, how do we decide which creatures truly belong to the dinosaurian lineage? When many of us picture the Mesozoic era, we imagine a single parade of giants. But not every giant from this ancient world was a dinosaur. The sky was ruled by pterosaurs, from tiny bat-sized gliders to colossal Quetzalcoatlus with wingspans rivaling a small plane. The seas belonged to marine reptiles like long-necked plesiosaurs and powerful mosasaurs, predators that never set foot on land as adults. Even before dinosaurs rose, mammal-like synapsids dominated the Permian and early Triassic, more closely related to us than to any reptile. Impressive, formidable, but none of these were dinosaurs. So what marks a true dinosaur? It is not just size, teeth, or ferocity. It is a specific body plan. Dinosaurs carried their limbs straight under the body, like living pillars, rather than sprawling out to the sides. Their hip socket was open and perforated, forming a deep cup that locked the femur into an upright stance. Their ankles formed a stable hinge for efficient forward motion, and their skulls shared characteristic openings that lightened the head and anchored powerful muscles. These details sound small, yet together, they set the stage for a world of scale we can barely imagine. You can see the difference in posture today. Watch a crocodile walk. Its legs splay outward, its belly close to the ground, every step a sideways push. Now picture an ostrich or a large bird striding across a field, body lifted high, legs swinging like pendulums beneath it. That upright, energy-efficient gait is much closer to how most dinosaurs moved. When we step back hundreds of millions of years and place those pillar-like limbs under early dinosaur bodies, we are watching a revolution in locomotion. Within this new design, evolution split dinosaurs into two great hip architectures. Saurischians, the so-called lizard-hipped dinosaurs, kept a hip layout somewhat similar to other reptiles and include the long-necked sauropods and the meat-eating theropods. Ornithischians, the bird-hipped dinosaurs, rotated the pubis backward, parallel to the ischium, a change linked to powerful herbivorous guts in groups like stegosaurs, ankylosaurs, and horned ceratopsians. The twist is profound. Real birds, the only dinosaurs that survived the end Cretaceous extinction, actually descend from the lizard-hipped theropods, not from the bird-hipped branch. Names can mislead. Bones do not. Why does all of this anatomy matter for size? Those upright limbs and reinforced hips allowed weight to travel straight down into the ground, turning living animals into walking columns capable of supporting tens of tons. Efficient, forward-focused ankles and balanced bodies let them move those colossal frames without exhausting themselves. Join us as we follow this blueprint into the Jurassic and Cretaceous, where it will be pushed to its limits in sauropods with necks longer than buses and theropod predators among the biggest creatures to ever walk the Earth. How far could this design be scaled up before biology itself said, no farther? To see how far that blueprint was pushed, we need to zoom out. We need to see the entire age of dinosaurs at once, stretched across deep time like layers in a cliff. This is the Mesozoic era in one glance. From about 252 million years ago to 66 million years ago, it spans roughly 186 million years of Earth history, but the dinosaurs' main reign fills around 165 of those. On a simple time bar, we divide it into three great periods. First, the Triassic, from about 252 to 201 million years ago. Then, the Jurassic, from 201 to 145 million years ago. Finally, the Cretaceous, from 145 to 66 million years ago, ending in one of the most dramatic mass extinctions our planet has ever seen. Imagine that time bar as a towering rock wall beside you. At the base, in the Triassic layers, Earth is still recovering from the greatest extinction in its history. The climate is hot, often harsh, with wide deserts and strong seasonal swings. All the continents are fused into one colossal landmass, Pangaea, surrounded by a vast global ocean. Here, small, agile reptiles are experimenting with new body plans. The first true dinosaurs appear. Lightly built hunters like Chelophysis and early herbivores such as Plateosaurus. This is a world of experimentation, where being small, fast, and flexible is the key to survival. Higher up the cliff, the colors change. We enter the Jurassic. Pangaea begins to split, and new coastlines, rift valleys, and shallow seas open up. The climate becomes more humid and generally warm, with lush forests of conifers, tree ferns, and towering cycads. This is the golden age of the giant sauropods. Creatures like Brachiosaurus and Diplodocus dominate the landscapes, their necks sweeping through different feeding heights to share the forests without direct conflict. Theropod predators grow larger to track this new abundance, and in the branches above, small feathered dinosaurs give rise to the first true birds. The blueprint of gigantism we have outlined is now fully expressed. At the top of the wall, the Cretaceous layers record a different world again. Continents are more separated, sea levels are high, and shallow inland seas flood the interiors of many landmasses. Flowering plants spread, reshaping ecosystems and offering new food sources. Dinosaurs respond with specialization and an evolutionary arms race. Horned giants like Triceratops, armored ankylosaurs, swift raptors, and colossal predators such as Tyrannosaurus rex share a planet rich in regional dinosaur faunas. All along this cliff, climate, sea level, and geography are shifting under the dinosaurs' feet. Their evolution is locked to those planetary changes. Join us as we step back hundreds of millions of years and move period by period into this ancient world of scale we can barely imagine. to see exactly how each chapter set the stage for the biggest creatures to ever walk the Earth. What did it feel like to stand in each of these ages? And how did those changing worlds drive bodies towards such extraordinary size? To feel that first age, we have to strip the Earth almost bare. No forests of towering conifers, no herds of colossal sauropods, not yet the biggest creatures to ever walk the Earth. Instead, we stand in the early Triassic, in the long shadow of an extinction that nearly ended complex life altogether. The Permian-Triassic mass extinction had just ripped through the biosphere, erasing around 90% of marine species and most land vertebrates. In its aftermath, the planet is quiet, but not peaceful. Pangaea dominates the map, a single supercontinent stretching almost from pole to pole, surrounded by a vast global ocean. When land is fused into one massive block like this, its interior lies far from any moderating sea. Summers in those continental hearts are scorching. Winters can be bitterly cold. Rainfall is seasonal and unreliable, and enormous desert belts sprawl across the low latitudes. This is a world of extremes. The atmosphere is loaded with carbon dioxide, the climate is unstable, and ecosystems are still reeling from their near collapse. Soils are thin, food chains are short, and recovery is patchy. In some places, landscapes burn under relentless sun. In others, flash floods tear through dry valleys, stripping away what little life has managed to return. It is hard to imagine giant dinosaurs surviving here. That is precisely the point. Before evolution can build giants, it must first rebuild resilience. Across this harsh terrain, hardy plants make the first move. Low, scrubby lycophytes and seed ferns cling to river margins and disturbed ground. Early conifers begin to stitch together the first real woodlands, sending roots into unstable soils and slowly anchoring entire ecosystems. These are not yet lush Jurassic forests. They are more like scattered green oases in a dominantly brown and red landscape, but they set the stage for everything that follows. Among the animals, it is the survivors and opportunists that rule. One of the most successful is Lystrosaurus, a stout, tusked herbivore with a beak for cropping tough plants. In some early Triassic fossil beds, almost every land vertebrate skeleton belongs to this single genus. Amphibians, too, endure in rivers and lakes. Long-bodied temnospondyls lurk in murky shallows, waiting for anything small enough to swallow. This is not yet an age of elegant specialization. It is an age of make do or die. Then, quietly at first, a new group begins to diversify. The archosaurs. These are the distant relatives of both crocodiles and dinosaurs. And in the Triassic, they experiment with form in spectacular ways. Some become crocodile-like predators with sprawling bodies and armored backs, patrolling riverbanks and floodplains. Others rise up onto their hind limbs, evolving into small, agile bipeds that can sprint across hot, open ground. In a world where shade is rare and resources are scattered, being light, fast, and adaptable is far more advantageous than being huge. Here, in these stressed ecosystems under a brutal sky, the blueprint for the dinosaur body plan is tested. Not in giants yet, but in quick, wary animals weaving through conifer shadows and along river margins. Join us as we follow these early archosaurs forward in time, into the late Triassic, when a few of them will cross an evolutionary threshold and begin the transformation from survivors into the first true dinosaurs. In the fading heat of the late Triassic, the blueprint finally crosses that threshold, not in the form of colossal plant-eating giants, but in quick, lightweight hunters, darting through fern thickets and along riverbanks. If we step back hundreds of millions of years to these first true dinosaurs, we do not find the biggest creatures to ever walk the earth. We find experiments. On the floodplains of what is now Argentina, a small, wiry animal threads between conifer roots. This is Eoraptor, one of the earliest known dinosaurs, barely a meter long from snout to tail. Its skull is lined with sharp, slightly different shaped teeth, suggesting an omnivorous diet, snapping at insects, small vertebrates, and perhaps soft plant material. Its body is lightly built, its forelimbs still useful for grasping, its hind limbs already long and powerful. When it runs, the spine levels, the tail stiffens as a counterbalance, and an unmistakably dinosaurian stride unfolds. Sharing these same landscapes is Herrerasaurus, a more imposing but still modest predator by later standards. At around 4 to 5 meters long, it is long-skulled and deep-chested, with blade-like teeth and strong jaws designed for tearing flesh. Yet even this early carnivore is not a top ruler of its world. It moves warily between the shadows of much larger archosaur relatives, careful not to draw the attention of the true Triassic super-predators. Because in this era, dinosaurs are just one branch on a broader archosaur family tree. Massive Rauisuchians, some the length of a bus, prowl on pillar-like limbs, their heads riding high above the ground. In river channels and swampy backwaters, long-snouted phytosaurs lurk, crocodile-like ambush hunters with eyes and nostrils placed high on their skulls. In many regions, these crocodile-line predators dominate the food chains, while early dinosaurs remain small, fast, and relatively rare. So why do these minor players matter? Their bodies hide crucial advantages. Dinosaurs stand with an upright, pillar-legged posture, limbs tucked directly beneath the body instead of sprawling to the sides. This alignment allows a more efficient stride, longer steps, and less wasted energy with each footfall. Their bones are lightly built, their tails and hips designed for balance, and many researchers suspect they carried a higher metabolic rate, perhaps closer to modern birds than to living reptiles. These traits let them run farther, stay active longer, and exploit open, drier habitats that might exhaust their competitors. A little later in the Triassic, we see this design refined in Chelophysis. Slender, hollow-boned, and over 2 meters long, it races along seasonal rivers in what is now the American Southwest. Narrow jaws armed with needle-sharp teeth snap at lizards, small archosaurs, and perhaps even the young of its own kind. Trackways and bone beds suggest groups moving together, hinting at pack hunting, or at least loose social behavior. Here, the dinosaur blueprint is no longer just an experiment. It is beginning to succeed. Yet even now, these animals are not rulers of their world. They are scattered, often small, still living in the shadows of other archosaur predators. To truly set the stage for a world of scale we can barely imagine, something else must happen. Another environmental crisis will soon sweep across Pangaea, reshuffling ecosystems once again and opening the door for dinosaurs to surge from the margins into dominance. Another environmental crisis does come, and when it hits, it does not arrive quietly. Around 201 million years ago, at the very end of the Triassic period, the ancient world lurches into yet another mass extinction, one powerful enough to tear down entire ecosystems and clear space for a new order of giants. We step back hundreds of millions of years to a Pangaea on the brink. Vast rift valleys split the supercontinent as the Atlantic Ocean begins to open. Along these rifts, something colossal stirs beneath our feet. Massive volcanic eruptions linked to what we now call the Central Atlantic Magmatic Province pour out lava in repeated pulses, building thick basalt plateaus while releasing staggering amounts of carbon dioxide and other gases into the atmosphere. This is not a single explosion. It is an era of fire. For hundreds of thousands of years, eruptions flare, fade, and flare again. Each pulse loads the air with CO2, driving rapid greenhouse warming, then cooling as aerosols and dust dim the sun. Oceans absorb that carbon, becoming more acidic, stressing marine life that builds shells and skeletons. On land and at sea, food webs fray. Many cannot keep up with the pace of change. The extinction that follows is selective, not random. Large crocodile-line archosaurs that once dominated as top predators and armored herbivores are hit especially hard. Many marine reptiles, including long-necked plesiosaurs' early relatives and fish-like ichthyosaurs, suffer severe losses. Whole groups of amphibians and early mammal relatives disappear. Vast ecological roles: apex hunter, bulk plant eater, mid-level omnivore, suddenly stand vacant across Earth. Yet the dinosaurs, still mostly small to medium-sized, fast and adaptable, weather the storm. Why them? Their lightweight, air sac-filled skeletons, efficient lungs, and high activity levels may have given them an edge in unstable climates. Generalist diets and rapid growth could help them exploit patchy resources when specialized competitors vanish. Not every dinosaur lineage survives, but as a group, they emerge from the crisis relatively intact, poised, rather than broken. With the worst of the end Triassic extinction behind them, the early Jurassic opens like a second chance. Join us as we watch dinosaurs surge into the empty spaces. Formerly minor theropods expand into apex predators. Early sauropodomorphs, once modest plant eaters, begin to push upward in size, testing the limits of what a land animal can be. In just a few million years, body sizes climb, diversity blossoms, and the foundations for the biggest creatures to ever walk the Earth are laid. This turning point reminds us that dinosaur dominance is not simply a story of superiority. It is a story of timing, of survival through repeated planetary crises, and of being in the right place when the world resets. So what happens when this newly cleared stage, rich with opportunity, meets the evolving bodies of sauropods and their kin? In the next chapter, we follow that collision of anatomy and environment as it begins to set the stage for a world of scale we can barely imagine. Now that the stage has been cleared by extinction and recovery, the scenery itself begins to move. Continents that once formed a single fused landmass start to crack, tilt, and drift. When we step back hundreds of millions of years to the early Jurassic, we do not just meet new dinosaurs. We watch the very map of the ancient world redraw itself. During this period, the supercontinent Pangaea begins to split apart, slowly dividing into a northern realm we call Laurasia and a southern realm known as Gondwana. Between these separating blocks of crust, new ocean basins open like widening scars, and long, jagged coastlines replace the smooth outline of a single colossal continent. What does this actually mean for life on the ground? It means that where there was once mostly interior land, there is now a growing fringe of shores, shallow seas, and humid margins. More coastline means more moisture. As warm waters circulate through these young oceans, they feed clouds and rainfall that penetrate deep into the continents. The climate, once marked by harsh seasonal swings and vast interior deserts, begins to soften. Temperatures remain warm, but extremes lessen. Fewer searing droughts, fewer frozen nights. Instead, broad belts of relatively stable, humid conditions spread across much of the Jurassic Earth. In this gentler framework, plants seize the opportunity. Conifer forests rise, their needle-laden branches forming dense, towering canopies. Beneath them, cycads cluster like giant prehistoric palms, while tree ferns grow into living umbrellas, some taller than a house. These are not scattered oases in a barren landscape. They are continuous, lush habitats stretching for hundreds of kilometers, a green engine turning sunlight into an immense, dependable food supply. For herbivorous dinosaurs, this is a revolution. Instead of scraping by on patchy vegetation, they now move through forests and floodplains rich in leaves, fronds, and shoots. Join us as we imagine herds of early sauropods wading through fern meadows, necks sweeping methodically from side to side, feeding almost without pause. In such a world, being big is no longer a rare experiment. It becomes a viable strategy. At the same time, the breaking of Pangaea does something subtler, but just as powerful. As Laurasia and Gondwana drift apart, And as rifts and shallow seas carve up the land, populations of dinosaurs find themselves cut off from one another. Island chains form, peninsulas become miniature islands. Geographic isolation turns into an engine of evolution, encouraging regional faunas to diverge and experiment with new body plans. This combination of stable warmth, abundant vegetation, and separated habitats helps set the stage for the biggest creatures to ever walk the Earth. In the mid to late Jurassic, truly gigantic sauropods emerge, animals whose bodies stretch longer than modern aircraft and whose masses rival small whales. Their lungs and bones will adapt to move air efficiently and shed weight, but without this planetary resculpting, such scale would be far harder to sustain. Pattern interrupt. Imagine removing the continents and leaving only climate and food. Could such giants still evolve? Or do they depend on drifting land to shape their story? In our next section, we dive into those sauropod bodies themselves, exploring how anatomy and physiology rose to meet the opportunities this changing planet provided. To see how anatomy rose to meet that opportunity, we step back hundreds of millions of years into the heart of the Jurassic. Before humans, before cities, before history itself, broad river plains shook under the footsteps of giants. Not just big animals, but true titans. The biggest creatures to ever walk the earth were gathering on fern-choked floodplains and conifer-shadowed valleys. This was the rise of the long necks. Early in the period, forms like Cedosaurus were already stretching the limits of size, bodies as long as a city bus, and weighing more than a dozen elephants. Later, more specialized relatives, such as Diplodocus and Apatosaurus, extended that blueprint even further, reaching lengths of 20 to 27 meters, comparable to 2 or 3 buses parked nose to tail, or a small apartment building laid on its side. Their basic body plan was deceptively simple. Tiny, lightweight heads perched at the end of extremely long necks, barrel-shaped bodies housing vast lungs and fermenting guts, tails that could equal or exceed the neck in length, tapering into whip-like tips, and beneath it all, columnar limbs that function like living support pillars, more like the straight posts of a bridge than the bent legs of a mammal. This design set the stage for a world of scale we can barely imagine. Why such immense necks? With a single step, a sauropod moved its entire feeding platform. By sweeping its head in wide arcs, it could crop leaves across a huge area without dragging that colossal body more than a few meters. Long necks allowed different species to specialize on different feeding heights, turning vertical space into ecological real estate. Some reached high to the crowns of conifers and seed ferns. Others held their necks more horizontally, combing low shrubs and ground-level vegetation. Picture a Jurassic floodplain at dawn. Mist hangs over braided rivers. Herds of Diplodocus wade through knee-deep water, necks held out like cranes, stripping soft plants along the banks. Nearby, more robust Apatosaurus bodies move through drier ground, their slightly higher reach pulling down tougher branches. In the background, a heavier, high-browsing form like Brachiosaurus lifts its shoulders above the rest, front legs taller than the back, raking foliage 5 or 6 stories above the ground. Is this not a three-dimensional forest divided into feeding layers? These animals pushed biological limits on an unprecedented scale. Supporting that weight required limb bones shaped like reinforced columns and vertebrae laced with air-filled spaces to cut mass without sacrificing strength. Pumping blood up those necks demanded powerful hearts and high blood pressure solutions we are only beginning to model. Managing heat in such massive bodies called for efficient, bird-like lungs and perhaps behavioral tricks, seeking shade, catching breezes, or using sheer bulk to smooth out temperature swings. How did extinction ever catch up with such successful designs? Join us as we move from this living architecture of pillars and cranes into the hidden machinery inside them, exploring muscles, lungs, and bones to see how physiology itself made such colossal scale possible. We have met the pillars and cranes of sauropod design. Now we step back hundreds of millions of years into the forests where one particular crane rewrote the skyline of the Jurassic world. This is Brachiosaurus and its close relatives like Giraffatitan. Not just long-necked dinosaurs, but high-browsing specialists that pushed vertical living to an extreme. While most sauropods balanced their bodies like giant seesaws, Brachiosaurus was different. Its front legs were longer than its hind legs, tilting the entire torso so the neck rose on an upward sweep, like a living construction crane reaching into the canopy. That unusual posture set the stage for a new way of being a giant. In raw numbers, these animals were colossal. Estimates suggest a length of roughly 20 to 25 meters from nose to tail. The head might have hovered 12 or even 13 meters above the ground when the neck was raised, as high as a 4-story building. In terms of mass, we are looking at the equivalent of several African elephants combined, tens of tons of living bone, muscle, and lung. When we speak of the biggest creatures to ever walk the earth, this is what we mean in concrete form. Why grow so high? High browsing opened up an entire layer of food that almost no other herbivores could touch. In a Jurassic ecosystem, filled with stegosaurs, smaller sauropods, and early ornithopods, most mouths pulled leaves from waist height to a few meters up. Brachiosaurus could simply reach over them, stripping foliage from the upper canopy, turning the tallest branches into its personal feeding ground. By climbing the forest vertically rather than competing on the ground, these giants reduced direct competition and carved out a towering niche of their own. To understand their impact, we have to picture Jurassic forests not as uniform walls of trees, but as multi-layered green architecture. Low shrubs and ferns formed a dim understory. Above that, mid-level branches created a second story of leaves. High overhead, crowns of conifers and seed ferns wove together into a dense canopy. Join us as we imagine herds of Brachiosaurus moving through this living cathedral. Their chests and shoulders would have parted trunks and branches. Their necks would have probed high boughs, snapping limbs, opening shafts of sunlight down to the forest floor. Over years and generations, that kind of feeding pressure could reshape entire landscapes. Repeatedly, pruned treetops might grow taller, with foliage clustered out of reach of smaller browsers. Trails beaten by massive feet could become semi-permanent clearings. Dinosaur highways, where light-loving plants flourished in their wake. The forest was not just a backdrop, it was a dynamic partner in the evolution of these giants. Yet an even deeper mystery rises with that long neck. How do you pump blood to a brain perched 13 meters above the heart without bursting vessels, overheating, or collapsing under your own weight? What hidden machinery of hearts, lungs, and air-filled bones made this impossible-seeming lifestyle real? To understand that hidden machinery, we have to look down, away from the clouds and necks, to a very different kind of Jurassic giant. Not a skyscraper on legs, but a walking fortress. Stegosaurus steps into view. About 9 meters long, low-slung, and broad-bodied, it carries a double row of tall, leaf-shaped plates along its back and a muscular tail ending in 4 wicked spikes. The head is small, the neck short, the forelimbs shorter than the hind limbs, tilting the whole body forward in a slow, deliberate posture. This is not a sprinter. This is a tank built for a world of teeth. Those plates are the first thing your eye follows. They rise from the neck to the hips, each one as tall as a person, thin and blade-like, rather than solid slabs of bone. For decades, paleontologists have asked, what were they actually for? Were they shields, radiators, billboards, or all three at once? In an ancient world shaped by predators, every surface of the body becomes an opportunity for survival. One hypothesis sees the plates as thermal machinery. Inside many plates, we find a lacework of blood vessel grooves, suggesting warm blood once flowed close to the surface. Turn broadside to the sun, and you absorb heat. Face the wind, and you shed it. Another idea emphasizes communication and recognition. In herds of similar-looking herbivores, a distinctive skyline of plates could help individuals recognize their own kind, or even signal age and status. Yet there is also display in the most dramatic sense. A stegosaurus that flushes blood into those plates might have turned them a deeper red or darker tone, suddenly appearing larger and more imposing. Imagine a hungry theropod testing the edge of a herd. The plates rise like a jagged wall, tails lift, spikes swing. Is this worth the risk? In a world of scale we can barely imagine, bluff and intimidation can be as powerful as armor. Stegosaurus was not alone in this defensive revolution. Early ankylosaurs in the Jurassic, such as primitive relatives of the later clubtail tanks, were already layering bony scutes into their skin, building the first true body armor that would one day produce some of the most heavily protected animals to ever walk the earth. Small ornithopods, lightly built plant eaters, explored speed, sharp senses, and perhaps camouflage instead of heavy plating. Different lineages, different answers to the same deadly question. That question came on two powerful legs, with jaws full of serrated teeth. Allosaurus and its kin were the apex predators of this period, with flexible necks, strong hind limbs, and grasping claws. Their skulls were built to open wide and drive blade-like teeth into flesh. As these hunters refined their weapons, herbivores responded with their own evolutionary engineering. Join us as we freeze a single encounter. A lone Allosaurus lowers its head and charges. The ground trembles. A Stegosaurus wheels sideways, presenting its flank. At the last instant, the tail whips around in a blur. One spike slams into the predator's thigh, perhaps even breaking bone, as some fossil injuries suggest. The hunter staggers back, bleeding, recalculating the cost of its next meal. This is the arms race written in bone. Every plate, spike, and scar a record of pressure from the carnivores that stalked Jurassic forests. And as we move forward in time, into the Cretaceous, these defenses will only escalate. Sprouting horns, frills, and full-body shields in a final, extravagant flourish before extinction reshapes life on Earth once again. But every shield invites a sharper spear. For every plated Stegosaurus or whip-tailed Diplodocus, something in the shadows was testing those defenses, probing for weakness, refining new ways to kill giants. In the late Jurassic, one predator stands above the rest: Allosaurus. This was the quintessential Jurassic apex hunter, ruling floodplains and conifer forests from North America to possibly Portugal. Adults stretched roughly 8 to 10 meters from snout to tail, comparable in length to a city bus, yet they were not lumbering brutes. Allosaurus carried a relatively lightly built skull atop a powerful neck, a design that favored speed and slashing over the bone-crushing force we will later see in tyrannosaurs. Look closely at that head, and the killing toolkit becomes clear. The jaws were lined with recurved, serrated teeth, like rows of steak knives built to slice through flesh rather than pulverize bone. Behind them, massive neck muscles anchored to strong vertebrae allowed the skull to swing down in powerful, hatchet-like blows. The forelimbs, unlike the shrunken arms of Tyrannosaurus rex, were still useful weapons. 3 clawed fingers capable of grasping, raking, and holding struggling prey. Join us as we imagine this animal not as a movie monster, but as a highly tuned product of evolution, built to bring down some of the biggest creatures to ever walk the earth. How do you hunt something many times your own mass? In a world dominated by colossal sauropods, Allosaurus likely relied on strategy as much as strength. Some bone beds preserve multiple Allosaurus individuals alongside large herbivores, hinting at possible group or at least opportunistic pack hunting. Ambushes near river crossings or waterholes would have favored a sudden rush from cover, jaws and claws targeting the flanks of a thirsty Camarasaurus. Juveniles and injured adults, rather than the healthiest giants, were almost certainly preferred targets. This was calculated risk in an ancient world where a single misplaced kick from a sauropod could shatter ribs and end a predator's career. When we compare Allosaurus to later tyrants like T-Rex, we see two different solutions to the same deadly problem. Tyrannosaurus evolved a deeper, massively reinforced skull, a bite force capable of crushing bone, and reduced forelimbs, turning its entire head into the primary weapon. Allosaurus, by contrast, seems adapted for repeated slashing attacks, using its lighter skull and flexible neck to open deep wounds and bleed prey out over time. Both were apex predators, but they filled distinct ecological roles in different chapters of the Mesozoic era. These Jurassic hunters never reached the extreme bulk of later Cretaceous megapredators, yet they did not need to. Their size, speed, and coordination were already sufficient to police ecosystems packed with giants. Predator-prey dynamics were driving evolutionary innovation on both sides of the arms race, setting the stage for the even more specialized, regionally distinct carnivores that would emerge as continents drifted further apart and new worlds of scale we can barely imagine took shape in the Cretaceous. As Jurassic predators refined their speed and senses, another quieter revolution was unfolding above their heads. Not in the colossal jaws of the biggest creatures to ever walk the earth, but in delicate filaments and spreading wings that would eventually turn one lineage of killers into something entirely new. To see that transformation, we travel to the late Jurassic limestones of what is now Germany. Here, in lagoonal mud once walked by small theropods, we meet Archaeopteryx. At first glance, it looks like a bird. Broad wings, asymmetrical flight feathers, a wishbone to help anchor the muscles of the chest. Yet look closer and the illusion breaks. It has sharp teeth set in its jaws, 3 clawed fingers on each hand, and a long, bony tail more like a small dinosaur than any modern robin or eagle. Archaeopteryx is a mosaic, a snapshot of evolution mid-stride. For a long time, feathers were treated as a symbol of birds alone. Now we know they run far deeper into the dinosaur family tree. In Jurassic and slightly later rocks of China, exquisitely preserved small theropods reveal bodies cloaked in simple filaments and branching plumes. Some, like Anchiornis, had long feathers on both arms and legs, forming four-winged profiles that blur the line between running dinosaur and gliding bird. Others carried fan-like tails or elaborate head crests that seemed built to be seen. Why would a predator evolve feathers long before true flight? Insulation is one powerful answer. On a cooling planet with active, high-metabolism hunters, a fuzzy coat will help lock in heat. Display is another. In an ancient world already filled with visual signals, bright or patterned feathers could advertise strength, attract mates, or intimidate rivals. Even simple arm feathers might have helped small theropods maneuver as they sprinted, braking or pivoting with more control. Only later were these structures co-opted, refined, and stretched into the aerodynamic surfaces that could lift a body from the ground. Early flight was not a single leap from earthbound runner to soaring master. It was a spectrum. Some feathered dinosaurs likely climbed and glided from tree to tree. Others may have used flapping wings to steady themselves as they dashed up steep slopes. A behavior echoed today when young birds use wing-assisted running to scramble onto logs and rocks. Still others experimented with parachuting descents or short, frantic bursts of powered flapping. Can we really draw a sharp line and say, here's the first true bird? Join us as we recognize the deeper implication. These Jurassic experiments tell us that birds are not merely descended from dinosaurs. Birds are dinosaurs, the only branch of this once colossal family still alive. Every pigeon, hawk, and hummingbird carries the legacy of theropod claws and teeth, rewritten in beaks and feathers. As we step back hundreds of millions of years to watch the Mesozoic unfold toward its catastrophic end, this connection will matter. Because when extinction comes, not every dinosaur will vanish. Which ones make it through, and why does flight tip the balance? The answer begins with a surprise. The dinosaurs that will survive the final catastrophe are already in the air, but the ground beneath them is changing into something entirely new. As we leave the Jurassic behind and enter the Cretaceous, the map of the ancient world starts to look strangely familiar. Pangaea is long gone. Instead of one colossal supercontinent, we now see separated blocks. A northern realm with North America and Eurasia, a southern realm with South America, Africa, India, Antarctica, and Australia. Wide, shallow epicontinental seas spill over low-lying interiors, turning what used to be solid land into sunlit seaways filled with plankton, ammonites, and marine reptiles. These seas do more than redraw coastlines. They raise global sea levels and help lock the planet into a generally warm state. Polar ice is greatly reduced, perhaps absent for long stretches, and heat circulates efficiently from equator to poles. In some high-latitude regions, temperate forests extend almost to the polar circles, with conifers and ginkgos enduring months of twilight, but not deep, permanent ice. Imagine standing in a polar forest and hearing dinosaurs moving through the undergrowth, where today only tundra and ice would stretch to the horizon. This warmth creates a different kind of cradle for giants. Humid coastal plains, island chains, and flooded continental interiors offer long-growing seasons and lush vegetation. The biggest creatures to ever walk the earth still find plenty to eat, but the menu is about to change in a fundamental way. In the mid-Cretaceous, a botanical revolution begins. Flowering plants, or angiosperms, appear and then rapidly diversify. At first, they are small, often overshadowed by towering conifers and cycads, but their strategy is powerful. Enclosed seeds, fruits, and showy flowers that recruit insects, birds, and other animals as partners. As angiosperms spread along rivers, floodplains, and forest edges, they gradually transform ecosystems, creating patchier, more complex habitats with new food sources at many levels. Join us as we watch herbivorous dinosaurs respond to this shift. Some adapt to browsing low, leafy angiosperm shrubs. Others continue to exploit older plant groups, but now in mosaics of forest and open ground. This coevolutionary dance between plants and plant eaters will help set the stage for a world of scale we can barely imagine, where specialized jaws, beaks, and gut systems track the rise of new vegetation. Meanwhile, the breakup of continents isolates dinosaur populations. Over millions of years, this separation drives regionalization. South America breeds its own colossal titanosaurs and apex predators. North America hosts different massive hadrosaurs and horned dinosaurs. Asia becomes a laboratory for sickle-clawed hunters and feathered forms. Africa and India follow their own evolutionary paths. The age of uniform dinosaur faunas is over. The age of provincial dinosaur worlds has begun. With new plants, new landscapes, and separated continents, evolutionary pressures intensify. The Cretaceous is where the arms races peak. Enormous theropods honing bone-crushing bites. Herbivores evolving heavier armor, longer horns, and elaborate crests that signal across herds. Social behaviors grow more complex as sight, sound, and display become weapons as critical as teeth and claws. How far can this escalation go before the entire system becomes fragile? We are approaching the final act, where these specialized Cretaceous titans will face a sudden test no adaptation can fully prepare them for. That escalating arms race does not just reshape predators and armor. It reshapes the very giants that define this age. As the Cretaceous period unfolds, a new dynasty of long-necked herbivores rises, the titanosaurs. These are not simply Jurassic sauropods copied and pasted into a later era. They are the last and, in many cases, the largest of the biggest creatures to ever walk the Earth. Join us as we step back hundreds of millions of years to South American floodplains, where names like Argentinosaurus and Patagotitan hint at a world of scale we can barely imagine. Individual animals may have exceeded 30 meters from nose to tail, with masses rivaling or surpassing any land animal known. Yet these record breakers come to us as puzzles. Many titanosaurs, including Argentinosaurus, are known from only a handful of vertebrae, ribs, and limb bones. No towering museum-ready skeleton, just fragments weathering from Cretaceous rock. From these pieces, paleontologists extrapolate whole bodies, using limb bone thickness and comparisons with better-known relatives to estimate size. Are the numbers exact? No. But even conservative reconstructions yield creatures as long as airplanes and heavier than a dozen African elephants combined. Anatomically, titanosaurs push sauropod design in new directions. Their chests are broader, giving them a more barrel-like profile. Their limb bones are especially robust, thick columns of bone that spread out the colossal forces of each step across a wider base. In several species, such as Saltosaurus, the skin carries bony plates called osteoderms, forming a mosaic of armor embedded in the flesh. This is a very different silhouette from the relatively gracile diplodocids of the Jurassic. It suggests a lineage experimenting with protection, weight distribution, and perhaps even mineral storage inside the body. Their world is changing as well. The supercontinent has broken apart, and titanosaurs roam warm, semi-arid floodplains, open woodlands, and patchy forests across South America, Africa, India, and beyond. Seasonal rivers swell and shrink, leaving broad flats of mud and fresh vegetation. Herds of these giants likely move slowly across the landscape, following new growth, stripping leaves from trees and high shrubs, and leaving behind trampled pathways that, in rare cases, survive as trackways pressed into ancient riverbanks. But there is a paradox at the heart of these animals. For all their size, every titanosaur begins life inside an egg that could fit in your two hands, often smaller than a soccer ball. How do you get from a fragile hatchling, barely taller than your knee, to a 70-ton adult towering over the canopy? What growth rates, what survival strategies, what parental behaviors make that journey possible in a dangerous ecosystem filled with mega-predators? Those questions set the stage for our next step into the biology of gigantism, where bone histology, nesting grounds, and the physics of growth will reveal how these Cretaceous titans raced against time itself to reach safety in sheer size. To understand that race against time, we need to look not just at how fast young giants grew, but at what waited for them if they failed. In the late Cretaceous, the landscape itself became an arms race, and herbivores answered escalating predator pressure with horns, frills, armor, and elaborate displays. This is the age of Triceratops and its kin. Before humans, before cities, before history itself, the Earth belonged to giants with faces turned into living shields. Triceratops carried a massive skull, nearly a third of its body length, a solid bony frill locked to the back of the head, and 3 forward-projecting horns that could reach the length of a grown person's arm. Not just head ornaments, but weapons and billboards. Those horns could drive into the ribs of a charging tyrannosaur, yet the same structures likely signaled age, health, and status to other Triceratops in the herd. Join us as we trace that dual purpose. Many ceratopsians show frills pierced by large openings, ringed with knobs and spikes, structures that would have lightened the skull while creating striking visual patterns. Did rival males clash horn to horn, or did they mostly posture, displaying vivid patterns of keratin and skin stretched over bone? Either way, evolution was sculpting skulls that balanced defense against colossal predators with the need to stand out to potential mates. Low to the ground, another answer to danger rolled slowly across the Cretaceous world. Ankylosaurs transformed the basic dinosaur body plan into a living tank. Their torsos were broad and flat, limbs splayed out to support heavy armor plates fused into a continuous shield, with rows of bony studs and spikes embedded in thick skin. At the tail's end, in species like Ankylosaurus, a massive bony club formed from fused vertebrae and osteoderms created a weapon capable of breaking bone with a single sideways swing, comparable in impact to a sledgehammer blow. Not every herbivore could rely on armor. Hadrosaurs, the duck-billed dinosaurs, followed a different path. They evolved battery-like jaws packed with hundreds of teeth for grinding tough plants, and in many species, elaborate crests that rose like helmets or swept back in long tubes over the skull. These crests were not just for show. Hollow chambers within them likely connected to the nasal passages, turning the entire head into a resonating instrument. A single call could have rolled across a floodplain like the horn of a distant ship. Imagine a coastal plain under a warm Cretaceous sun, shallow inland seas shimmering on the horizon. A mixed herd moves together, a phalanx of triceratops at the front, shields and horns forming a living wall, ranks of hadrosaurs in the middle, juveniles sheltered as adults raise their crests and trade low, haunting calls, ankylosaurs on the flanks, armor plates catching the light as heavy tail clubs sway in warning. Different bodies, different strategies, one shared problem: survive long enough to grow. These defenses and displays did not arise in isolation. They evolved under twin pressures: avoid becoming a meal for ever more powerful carnivores, and win the constant competition for mates and status within their own species. In that tension between teeth and attraction, between survival and spectacle, the Cretaceous set the stage for some of the most extreme body forms in dinosaur history. But how did the predators respond to walls of horns, armor, and organized herds? What kind of hunter can break a living tank or crack a horned phalanx wide open? The answer, in the very latest Cretaceous, was a skull with legs. On the floodplains of western North America, just before the final extinction, an apex hunter emerged that embodied the entire arms race in one colossal body. This was Tyrannosaurus rex, not just a big predator, but one of the biggest creatures to ever walk the earth that hunted on two legs. At around 12 to 13 meters from nose to tail, and weighing perhaps 6 to 9 tons, an adult T-Rex rivaled a city bus in length and a fully loaded truck in mass. Its head alone was a weapon system. The skull stretched over 1.5 meters, longer than many people are tall, packed with thick, banana-sized teeth, designed not for slicing delicately, but for crushing and tearing. When we say it had one of the strongest bite forces of any land animal known, we are not speaking in metaphors. Biomechanical models and crushed bones tell the story. A T-Rex bite could drive teeth through solid bone, leaving punctures and shattered fragments that we still see preserved in the fossils of hadrosaurs and horned dinosaurs. Before humans, before cities, before history itself, this ancient world echoed with the sound of those jaws closing. Not just sharp teeth, but a reinforced skull, a deep, thick neck, and massive jaw muscles turned each bite into an impact event. Some prey bones show healed T-Rex bite marks, clear evidence that these giants attacked living animals that survived the encounter, at least for a while. Other skeletons are chewed apart, vertebrae and hips scored with tooth grooves, showing that T-Rex also returned to carcasses as a powerful scavenger. Look at its proportions, and you see a predator specialized for this brutal strategy. A huge, heavy skull balanced by a long, muscular tail. Pillar-like hind limbs with robust thigh bones and strong feet, built to drive a multi-ton body forward in powerful strides rather than delicate sprints. The arms, by contrast, seem almost absurdly small, yet they were thick-boned and muscular, with only 2 strong claws. Far from useless, they may have helped the animal brace itself when rising, grip struggling prey at close range, or hold a carcass steady while the head did the real work. It is important to place T-Rex correctly in time. Join us as we step back hundreds of millions of years in our minds and remember that this predator did not stalk Jurassic sauropods or clash with Allosaurus. T-Rex lived only in the very latest Cretaceous, about 68 to 66 million years ago, and only in what is now Western North America. Allosaurus had vanished tens of millions of years earlier, separated from T-Rex by more time than lies between us and the earliest humans. So was Tyrannosaurus rex a hunter or a scavenger? The evidence points to both. A flexible giant exploiting any opportunity in a world of scale we can barely imagine. In the next section, we will set the stage for that world by looking closely at the prey itself. Armored tanks, horned phalanxes, and the herd strategies that tried to stand against the tyrant king. But not every killer in this ancient world was a colossal tyrant. Between the thundering feet of hadrosaurs and the crushing jaws of tyrannosaurs, another kind of predator moved in the shadows, small, feathered, and astonishingly quick. In the late Cretaceous, the dromaeosaurs, raptors, were among the most agile hunters on Earth. Names like Velociraptor and Deinonychus have become legend, yet our popular image of them is often wrong. The real Velociraptor was not a man-sized movie monster. It was closer to a turkey in size, around 2 meters from snout to tail, lightly built and almost certainly covered in feathers. Deinonychus was larger and more robust, but still far from the biggest creatures to ever walk the Earth, relying on speed and precision rather than brute force. What made these predators so formidable? Start with the feet. Each hind foot carried an enlarged, sickle-shaped claw on the second toe, held off the ground like a razor on standby, ready to slash or pin struggling prey. Add long grasping hands with curved claws, a stiffened tail acting as a dynamic counterbalance, and a skull packed with forward-facing eyes and a keen sense of smell. We are looking at hunters built for rapid acceleration, tight turns, and coordinated attacks in cluttered environments where a misstep could mean starvation or death. For a long time, feathers on dinosaurs seemed like a strange, almost decorative idea. Then the fossils began to speak. In exquisitely preserved rocks of China and elsewhere, paleontologists uncovered non-bird theropods with clear impressions of feathers or feather-like filaments. Not just early birds, but relatives of Velociraptor, of Deinonychus, and even some larger predators. These structures range from simple hair-like filaments to complex branching feathers, reinforcing the deep evolutionary link between classic raptor dinosaurs and the birds outside our windows today. When we step back hundreds of millions of years in our imagination, we are not watching scaly movie monsters. We are watching dynamic, feathered animals whose descendants still fill the skies. Raptors did not compete directly with tyrannosaurs for the same prey. Instead, they filled different ecological niches. Where a massive tyrannosaur might focus on adult hadrosaurs or ceratopsians in open floodplains, smaller dromaeosaurs could slip into forests and river margins, targeting juveniles, small ornithopods, lizards, and even carrion. Their speed and maneuverability made them ideal for ambush in dense undergrowth, or for harrying larger prey already weakened or isolated. Could some species have hunted in coordinated groups, using numbers to bring down animals far larger than themselves? The debate continues, but bone beds containing multiple Deinonychus individuals alongside the same prey species suggest at least some level of social or repeated group behavior. Join us as we slow time in a Cretaceous forest. Dawn light filters through towering conifers and flowering plants, painting the air with drifting dust and pollen. A herd of hadrosaurs moves cautiously along a riverbank, adults forming a living wall around their young. In the ferns at their feet, something watches. A pack of feathered dromaeosaurs, each no larger than a wolf, flows through the shadows. Plumage breaks up their outline, mottled patterns blending with leaf and branch. Tails held rigid for balance, sickle claws lifted. They fan out, using fallen logs and cycads as cover, One raptor darts forward, deliberately flushing the herd. Panic erupts. Juveniles stumble toward the trees, exactly where the others wait. In a burst of speed, the pack strikes from multiple angles. Claws hooking, hands grappling, teeth finding soft tissue at the throat and belly. The forest absorbs the sound, and then it is over. No roar, no cinematic duel, just swift, coordinated violence from predators perfectly tuned to their niche. These smaller hunters remind us that the Cretaceous was not only an age of giants, but a layered ecosystem where size was just one strategy among many. As we set the stage for the herbivore defenses that shaped predator evolution, from armor plates to interlocking horns, we must remember the raptors in the undergrowth, testing every weakness. In the next section, we will turn fully to those prey dynasties, the living fortresses and horned phalanxes that forced even the boldest carnivores to think before they struck. As we follow those living fortresses and horned phalanxes across ancient floodplains, we might imagine dinosaurs as creatures of endless sun and steaming swamps. But not all of their world was bright. Some herds marched into the long night. During the Cretaceous period, the poles were not the frozen deserts we know today. Continental positions and elevated greenhouse gases warmed high latitudes. So what is now Alaska, Antarctica, and southern Australia carried dense forests of conifers, ginkgos, and early flowering plants. Winters were chilly, with frost and even seasonal snow. Yet the most dramatic challenge was light itself. For weeks, even months, the sun barely rose. Imagine being a giant herbivore under a sky that never truly brightens. For a long time, many scientists assumed dinosaurs could not have lived that far north or south year-round. Reptiles, we thought, meant warmth, constancy, and migration. Then the rocks began to argue back. Join us as we step back hundreds of millions of years in imagination and walk the banks of ancient polar rivers where paleontologists have uncovered bone beds and trackways at astonishing latitudes. In Alaska's Prince Creek Formation, duck-billed hadrosaurs, horned dinosaurs, and small theropods left their bones in sediments laid down well within the Arctic Circle. In Antarctica and high southern Australia, fragmentary skeletons tell the same story. Dinosaurs were not visitors. Many were residents. What does it take to survive half a year of low slanting light and bitter nights? Not just size, not just thick skin. Some of these polar dinosaurs were relatively small, including fleet-footed theropods that show close ties to birds. Their fossils hint at insulating feathers or filamentous coverings, structures that would have trapped heat like a down jacket. Others, like the massive hadrosaurs, may have relied on deep bodies, strong circulatory systems, and perhaps elevated metabolisms to keep muscles and brains warm when the forest floor froze. Picture a polar Cretaceous forest. The canopy is a dark lattice of conifer branches and ginkgo fans dusted with rime. Snow lies in thin, wind-sculpted sheets between tree trunks. The air is cold, but not lethal, closer to a modern coastal winter than to today's Antarctic interior. In the dim blue-gray twilight, a column of hadrosaurs moves slowly along a frozen stream, their breath steaming, their hoof-like footprints pressing into crusted snow. Between the roots, small feathered hunters weave through shadow, alert eyes reflecting the faint light. This is not a tropical swamp. This is a world of scale we can barely imagine, where the biggest creatures to ever walk the earth endure months of dusk. Scenes like this force us to confront a deeper question. What were dinosaurs physiologically? Were they cold-blooded like modern lizards? Warm-blooded like birds and mammals? Or something in between? A spectrum of metabolisms tuned to climate and lifestyle? As we follow these polar herds back toward lower latitudes, we will step into that mystery and into the beating hearts of the giants themselves. To understand those beating hearts, we have to look at the frames that held them up. Before metabolisms, before growth rates, there is something even more fundamental: bone. Not just any bone, but skeletons engineered on a scale that, even today, feels impossible. Join us as we step back hundreds of millions of years and stand beneath a sauropod spine. At first glance, it looks massive, a solid beam of stone. It was not. Slice through one of those vertebrae, and you would see a honeycomb of chambers and struts, great pockets of air woven through dense bone. This pneumaticity, shared with the birds that still walk our Earth, made the backbone of the biggest creatures to ever walk the Earth both strong and astonishingly light, like a natural steel truss bridge rather than a solid concrete block. Before humans, before cities, before history itself, evolution was quietly running structural experiments. Air-filled vertebrae allowed sauropods such as Brachiosaurus or Argentinosaurus to carry necks longer than buses without collapsing under their own weight. The bone that remained was arranged in thin internal walls and arches, directing forces around those empty spaces, just as modern engineers lace cranes and radio towers with open lattices instead of solid metal. In a world of scale we can barely imagine, saving every kilogram mattered. Beneath that airy spine, the story changes. Limbs became thick, almost architectural columns, optimized to bear colossal compressive loads. The upper arm and thigh bones flared where they met shoulder and hip, spreading stress over broad surfaces. Knee and elbow joints locked into simple, stable hinges, trading agility for reliability. When a 50 or 70-ton giant took a step, those column-like legs behaved less like the springy limbs of a cat and more like the pillars of a temple, channeling forces straight down into the ground. How else could such a body move without snapping itself apart? Yet the real elegance appears where length meets balance. Sauropod neck and tail vertebrae were not just stacked like bricks. They were interlocked with complex bony struts, ridges, and overlapping processes. Long ligaments ran along the spine like tension cables, binding the series into a flexible but unified beam. This meant a neck could sweep through forests, and a tail could act as a counterweight or even a whip, without requiring impossibly huge muscles to hold them up every second of the day. In many ways, these skeletons resemble bridges more than typical animals. A suspension bridge spans a river with cables and towers, using geometry to tame gravity. A crane lifts heavy loads with a lightweight lattice boom. Dinosaurs converged on the same solutions: distribute forces, lengthen supports, remove unnecessary material. If you simply scaled up the body of a modern lizard, its solid bones would crush, its joints would fail, and it would be trapped in its own bulk long before reaching sauropod size. These structural innovations set the stage for everything that followed, for giant lungs, vast guts, and growth rates that pushed bone and blood to their limits. But even the best skeleton has to be powered. How did muscles, hearts, and respiratory systems keep pace with such ambition? In the next section, we will step inside those living engines and ask how you fuel a moving mountain. To power a moving mountain, you need more than big muscles. You need air. Not just more air, but a smarter way to use it. Deep inside these colossal bodies, evolution rewired the very act of breathing. For a long time, we imagined dinosaur lungs as scaled-up versions of our own. In and out, like a giant reptilian bellows. Yet their bones tell a different story. Along the vertebrae of many Saurischian dinosaurs, sauropods and the big theropods, paleontologists have found delicate hollows and chambers. These are not random gaps. They match the pattern of air sacs in modern birds, invading the skeleton and leaving behind a lacework of cavities in neck, back, and hip bones. Join us as we step back hundreds of millions of years and picture a sauropod's neck in cross-section. The bone is not solid. It is honeycombed and light and threaded with air. In life, those spaces were filled by a system of sacs connected to rigid lungs, forming a respiratory network that turned the entire torso into a living bellows. In the lab, CT scans of ostrich and chicken skeletons reveal the same architecture: air sacs ballooning between organs, slipping between ribs, and even pushing into the vertebrae. This bird-like system breathes in a very different way. Our mammal lungs use tidal flow. Air goes in, mixes, and then comes back out the same route. Dinosaurs with bird-style lungs likely enjoyed unidirectional airflow. Fresh air swept through the lungs in one direction, even during exhalation, as air sacs before and behind the lungs traded volumes like pistons. The result was continuous oxygen exchange, far more efficient than our stop-start pattern. What does that mean for the biggest creatures to ever walk the Earth? It means a heart and bloodstream constantly supplied with high oxygen air, feeding hard-working muscles and fast-growing bones. It means juvenile titanosaurs racing through growth stages without stalling for breath. It also means a powerful internal cooling system. As air moved through those deep sacs and hollow bones, it carried away heat from organs and muscle, preventing these giants from overheating under the Jurassic and Cretaceous sun. Here, we can use living birds as our guide. Watch an animation of air moving through a goose's lungs, or a CT diagram of an ostrich chest, and you are seeing, in simplified form, the same principle that may have pulsed inside a Brachiosaurus or a Tyrannosaurus. The connection is not just anatomical, it is physiological, a shared solution to the challenge of being active in a warm, ancient world. This respiratory upgrade did more than keep dinosaurs on their feet. It may have set the stage for true gigantism. With lightweight, air-filled bones and supercharged lungs, some lineages could push body size to extremes without suffocating under their own bulk. But breathing is only one side of the equation. In the next section, we will follow the blood itself and ask, how do you pump life through a neck longer than a bus? Breathing and blood could keep a giant alive. But how do you build that giant in the first place when it starts life smaller than a house cat? In the age of sauropods, the biggest creatures to ever walk the Earth did not begin as colossal calves. They began as eggs, not car-sized eggs, not even beach ball eggs. The fossil record tells us that even a 70-ton titan, like Argentinosaurus, hatched from an egg roughly the size of a soccer ball. This is not a guess of convenience. It is a hard physical limit. If the shell were much thicker, gases could not move in and out, and the embryo inside would suffocate before it ever met the ancient world. This paradox sets the stage for one of the most extreme growth stories in the history of life. How do you go from a hatchling that could fit in your arms to a body that could crush a truck under 1 foot? All within a few short decades. To answer that, we do not just look at bones from the outside, we slice them open. Under the microscope, dinosaur bones become forests of information. Fine growth rings, like those in a tree, record seasons of plenty and scarcity. Dense networks of blood vessel canals, called vascularization, reveal how fast new tissue was laid down. In many sauropods, these canals are abundant and chaotic, a signature of rapid, uninterrupted growth. Some individuals show that in perhaps 30 or 40 years, they went from a few kilograms to tens of tons. That is more like a supercharged mammal than a slow, cold reptile. Join us as we step back hundreds of millions of years to a nesting ground on a warm Jurassic floodplain. The air is heavy. The ferns are waist-high to us, but barely ankle-high to the adults. Shallow pits dot the ground in regular clusters, each filled with a dozen or more round eggs, layered and covered with vegetation. Now imagine not one nest, but hundreds, spread across the landscape. When they hatch, the scene transforms. Tiny, long-necked hatchlings, no taller than your knee, swarm between the pillar-like legs of their parents, a living tide of vulnerability beneath living towers of bone and muscle. Why so many small eggs, instead of a few large, well-protected young? In a predator-rich environment, numbers are a kind of armor. Most hatchlings will fall victim to small theropods, crocodile relatives, or even giant insects and mammals. A nesting colony might produce thousands of offspring, yet only a handful will survive to join the ranks of the giants. High juvenile mortality and rapid growth walk hand in hand. The faster a youngster escapes the size range of most predators, the better its odds. Such a life history demands constant fuel. Rapidly growing bones, active muscles, and developing organs require abundant, reliable food and an efficient physiology to extract energy from it. Lush plant communities, warm climates, and bird-like lungs may all have worked together to sustain this explosive growth. But even that was not enough on its own. To turn a soccer ball egg into a skyscraper of flesh, the heart itself had to rise to the challenge. In the next section, we will follow the pulse of a sauropod and ask, what kind of engine can drive a neck that scrapes the sky? The heart is only part of the story. A colossal body needs fuel, and how that fuel is burned changes everything. Before humans, before cities, before history itself, the Earth belonged to giants whose bodies ran on very different engines. Were those engines slow and cold, like a crocodile's, or hot and relentless, like a bird's? For more than a century, scientists have argued over a deceptively simple question. Were dinosaurs cold-blooded or warm-blooded? In modern terms, were they ectothermic, depending on external heat, like most reptiles? Or endothermic, generating high, constant internal heat, like birds and mammals? Or did they occupy something in between, a mesothermic state, with metabolisms elevated above lizards, but not quite at sparrow level? The answer helps set the stage for understanding how they powered such massive frames. To approach this mystery, we step back hundreds of millions of years and look inside the bones themselves. Under a microscope, many dinosaur bones show dense networks of blood vessels and growth rings that indicate rapid, almost uninterrupted growth, especially in young individuals. This pattern looks far more like the fast-growing bones of birds and mammals than the slower, seasonal growth of most modern reptiles. Fast growth demands energy. A lot of it. Predator-prey ratios offer another clue. In ecosystems dominated by slow, low-energy hunters, predators are rare, and prey animals are overwhelmingly abundant. Yet in many dinosaur fossil communities, the balance between meat-eaters and herbivores resembles that of modern high-energy systems with active endothermic predators. To sustain that many hunters, the entire food web must be running at a higher metabolic gear. Even the chemistry locked in ancient minerals speaks. Isotope data from dinosaur bones, especially oxygen isotopes, suggest relatively stable body temperatures over time and across different parts of the skeleton. In many species, this stability is difficult to reconcile with a purely ectothermic lifestyle that rises and falls with the sun. Instead, it points toward bodies capable of buffering temperature swings through internal heat, sheer size, or both. Here, scale itself becomes a kind of physiology. Many large dinosaurs, particularly sauropods, likely practiced what scientists call gigantothermy. Simply by being enormous, they lost heat very slowly, maintaining a fairly constant internal temperature even without the fully turbocharged endothermy of a small bird. A 50-ton animal changes temperature like an ocean, not a pond. This would have allowed these giants to function as living thermal reservoirs in a world of scale we can barely imagine. Yet not all dinosaurs were slow, heat-soaked behemoths. Active predators such as dromaeosaurs and fast-moving herbivores like hadrosaurs and some ornithomimids show limb proportions, muscle attachment scars, and growth rates that point to higher metabolic levels than any modern lizard. These were animals built for sustained activity, long-distance migration, and rapid bursts of speed. Could a cold-blooded engine truly drive such relentless motion? When we assemble these lines of evidence, a picture emerges of diverse, complex metabolisms. Some small species may have approached modern bird-like endothermy. Others, especially the largest, relied on gigantothermy and elevated, but not extreme metabolic rates. Overall, dinosaurs trended toward higher energy lifestyles, and when we combine that with their efficient, bird-style lungs, we begin to see how they could fuel both rapid growth and lifelong gigantism. Join us as we carry this idea forward. In the next section, we will follow the air itself, tracing how each breath moved through these colossal bodies and asking, what kind of respiratory system can keep the biggest creatures to ever walk the earth from simply running out of oxygen? To understand how those lungs and air sacs powered such vast bodies, we also need to understand the world those bodies lived in. Not just the animals, but the air, the water, and the plants that fed them. When we step back hundreds of millions of years into the Mesozoic era, we enter a greenhouse Earth. Global temperatures were generally warm from pole to pole, with no permanent ice caps, and winters that, in many regions, felt more like a mild modern autumn than a deep freeze. Atmospheric carbon dioxide was often several times higher than today, trapping more heat and supercharging photosynthesis. This was not a world of bare rock and sparse scrub. It was a world of scale we can barely imagine, where sunlight, warmth, and CO2 combined to turn vast landscapes into living factories of plant growth. At first glance, the menu for herbivorous dinosaurs might seem disappointing. The dominant plants for much of this era were ferns, horsetails, cycads, ginkgos, and conifers, not the rich mix of flowering grasses, shrubs, and broadleaf trees that support modern grazers. Many of these ancient plants were less energy-dense, with tougher fibers and more defensive chemicals. Yet their sheer abundance, height, and rapid continuous growth changed the equation. On a Jurassic floodplain, conifer forests stretched for hundreds of kilometers. Understory ferns carpeted the ground, and river margins were choked with horsetails taller than a person. For a herd of sauropods, this meant that even low-quality food, taken in colossal quantities, could sustain bodies heavier than a dozen elephants. High sea levels during much of the Jurassic and Cretaceous periods flooded the edges of continents, creating broad, flat coastal plains and networks of shallow inland seas. These conditions favored enormous river systems and seasonal wetlands, constantly depositing fresh sediments and nutrients. Join us as we picture these lowlands: braided rivers, shifting channels, and lush, water-fed vegetation stretching to the horizon. Such environments are ideal for large herds, much like the African savannas today. But in many places, the plant productivity of Mesozoic floodplains may have been even higher. This is where geography and climate together set the stage for gigantism. Warm, relatively stable climates persisted for millions of years at a time. Without repeated, continent-wide glaciations to reset ecosystems, plant and animal communities could reach long-term equilibria. Over countless generations, natural selection could push body sizes upward and keep them there, because the underlying resource base remained dependable. What happens when you give evolution that much time, that much warmth, and that much food? Paleontologists estimate that in some regions, the biomass of large herbivorous dinosaurs on a single floodplain could have rivaled or exceeded that of all the wildebeest, zebras, and buffalo on a modern savanna combined. Herds of sauropods, ornithopods, and armored dinosaurs transformed vegetation as they moved, yet the constantly renewing plant cover kept pace. In the next section, we will dive into how these crowded, food-rich landscapes actually worked, exploring the feeding strategies, migrations, and ecological roles that allowed the biggest creatures to ever walk the earth to share the same ancient world without exhausting it. These crowded, food-rich landscapes did more than feed giants. They armed them. Every bite of fern, conifer, or flowering plant was part of an invisible contest between hunter and hunted that would shape a world of scale we can barely imagine. When herbivores grew larger, they did not just become heavier, they became moving fortresses. A massive sauropod herd, each animal longer than a bus, could tower above most predators, using sheer size to deter attacks and long necks to reach untouched canopies. But evolution does not leave an advantage unchallenged. As plant eaters pushed upward and outward, predators were pressured to follow, evolving stronger jaws, sharper senses, and new ways to bring down living mountains. Join us as we step back hundreds of millions of years into the Jurassic, where this arms race is already well underway. On floodplains dominated by colossal sauropods like Diplodocus and Brachiosaurus, predators such as Allosaurus stalked the edges of the herds. Allosaurus did not match a sauropod in bulk, yet its skull, neck, and tail formed a powerful striking system, with serrated teeth and muscular legs built for bursts of speed. It may have targeted the young, the old, or the injured, turning the vulnerabilities of giant bodies into opportunities for survival. By the Cretaceous, these dynamics intensified. The breakup of continents and the spread of new plants set the stage for regional predator-prey duels. In western North America, Tyrannosaurus rex faced heavily armed herbivores like Triceratops and Ankylosaurus. Here, size was matched by weaponry. T-Rex carried one of the strongest bite forces in Earth's history, capable of crushing bone. Yet its prey responded with massive horns, bony frills, and tail clubs that could shatter bone in return. Was this simply a race to be bigger, or a race to be better defended? Not every winner in this ancient contest was enormous. Many lineages explored different solutions: armor plates in stegosaurs and ankylosaurs, horns and crests in ceratopsians, and the sheer speed and agility of ornithopods allowed smaller species to coexist alongside giants. Some relied on group living, turning many eyes and many bodies into a living shield. Others used dense forests, wetlands, or coastal zones as refuges, slipping into niches where the biggest creatures to ever walk the earth could not easily follow. Yet bigger was never purely better. Colossal bodies required vast territories, long growth periods, and slow reproduction. A single drought, a shift in plant communities, or a drop in temperature could stress these giants far more than their smaller, faster breeding neighbors. Mobility was limited, juvenile survival was critical, and dependence on stable ecosystems made them exquisitely powerful, but also exquisitely fragile. These trade-offs would matter when the Mesozoic's calm shattered. As climates fluctuated, seas advanced and retreated, and finally, as a cosmic impact darkened the skies, which strategies proved most resilient? In the next section, we will follow those final stresses step by step and ask why some dinosaur lineages vanished in the chaos, while a feathered few crossed the threshold into the next era. To follow those final stresses step by step, we have to face a deeper mystery. How do we know any of this happened at all? Before humans, before cities, before history itself, the Earth belonged to giants, yet all that remains of their colossal age is stone, dust, and clues. Those clues are fossils, not just bones locked in rock, but any preserved remains, impressions, or traces of ancient life. A fossil can be a femur thicker than your waist, or a single tooth. It can be a ribbed shell, a delicate skin impression, a line of footprints frozen mid-stride, or even a coprolite, fossilized dung that records what a dinosaur ate on a particular day in a vanished world. Each one is a time capsule from a world of scale we can barely imagine. Most of these time capsules form through a process called permineralization. When an animal dies in the right conditions, quickly buried by mud, sand, or volcanic ash, its soft tissues decay, but the harder parts like bone or shell remain. Groundwater rich in dissolved minerals seeps through, filling the tiny spaces inside. Over thousands, then millions of years, those minerals crystallize. The original tissue is replaced or reinforced, turning fragile bone into rock that can endure entire geological periods. Yet this transformation is rare. For fossilization to work, the body must escape scavengers, weather, and decay. That means certain environments, river deltas, floodplains, lake bottoms, and coastal seas, set the stage for preservation, while mountains, forests, and dry uplands often erase the dead without a trace. soft-bodied animals like many early reptiles, insects, and marine creatures almost vanish from the record, surviving only in a few exceptional deposits. Even for the biggest creatures to ever walk the Earth, we frequently find only fragments. A handful of vertebrae, a partial skull, a single massive limb bone. So how do we step back hundreds of millions of years and reconstruct full ecosystems from such scattered remains? Join us as we follow the rock itself. By reading stratigraphy, the ordered layers of sediment, we can tell which fossils are older or younger and link them to specific moments in the Mesozoic era. By comparing bones across related species, we can infer missing pieces, scaling from a well-known skeleton to a new fragmentary giant. Modern technology pushes this even further. CT scanning lets us peer inside skulls without breaking them, revealing brain cavities, inner ears, and sinuses that hint at senses and behavior. High-resolution imaging exposes growth rings in bones, like tree rings, showing how fast a sauropod grew, or when a predator reached adulthood. Suddenly, stone becomes biology again. Every fossil is a data point in a much larger puzzle, and that puzzle is still incomplete. With each new discovery, our picture of dinosaur evolution, behavior, and extinction sharpens, then shifts. What happens when a single new skeleton rewrites an entire branch of the dinosaur family tree? In the next section, we will watch that process unfold and see how fresh finds continue to reshape the story of the Age of Dinosaurs. But that reshaping does not happen in a museum office or a computer lab alone. It begins far from cities, in landscapes that feel almost as ancient as the bones we seek. Before the heat builds, before the wind begins to howl, a small team moves out across the Badlands at dawn. Headlamps click off as the sky turns pale. Packs are heavy with water. Rock hammers plaster GPS units and folded geological maps. We follow a faint trail along dry gullies and eroded cliffs, past bands of red, tan, and gray sediment that record an era when this quiet desert was a lush floodplain walked by the biggest creatures to ever walk the Earth. The only sounds now are footsteps on gravel and the distant call of a raven. How do we decide where to stop in this vast, empty world? The answer is part science, part memory, part chance. Geological maps tell us which layers formed in the Triassic, Jurassic, or Cretaceous, and which of those once held rivers, lakes, or coastal plains, where carcasses could be buried quickly. Old field notes mark places where a single bone once eroded out decades ago. Sometimes it is just a flash of white on a slope, the curve of a weathered fragment that does not look like ordinary rock at all. Join us as we kneel beside that fragment and begin the slow work of turning hint into skeleton. First, broad tools, small picks and chisels to peel back the overlying sediment, always leaving a protective buffer around anything that might be bone. Then, as the shape sharpens, we trade steel for delicacy. Brushes, wooden probes, even dental tools whisk grains of rock away one by one. Every few minutes, someone pauses to mark a point on a map, log a GPS coordinate, sketch the position of each exposed piece. It is meticulous. It is repetitive. It can feel for hours like nothing is changing. And then the pattern interrupts. A curve resolves into the rim of a sauropod vertebra, as wide as a dinner plate, its internal structure still showing the air-filled chambers that once lightened a colossal neck. Or a tiny glint appears in the dust, and a theropod tooth emerges, recurved and serrated like a miniature steak knife from a predator that stalked this riverbank in another period of Earth's history. In that moment, the distance between our world and theirs collapses. Once exposed and documented, the bones must travel. To survive that journey, we wrap them in a cocoon of the modern world. We cover fragile surfaces with protective foil or paper, build a cradle of damp plaster-soaked burlap around each block, and let it harden into a rigid jacket. Hours later, under a harsh afternoon sun, that white, plaster-wrapped package is lifted carefully into the back of a truck or slung beneath a helicopter if the terrain is too rough. From ancient riverbed to modern laboratory, the fossil begins the next stage of its story. And in the following section, we will step inside that lab to watch stone slowly give way to bone and data and discovery. Now the plaster jacket has done its job, and the fossil's journey turns inward. From blazing desert and roaring helicopter blades, we move into a quiet, controlled room filled with the soft hiss of air, the buzz of fluorescent lights, and tables lined with ancient bones still locked in stone. This is the preparation lab. Here, technicians sit for hours under microscopes, guiding needle-fine tools and tiny air scribes along the boundary between rock and fossil. Grain by grain, they peel away sediments that have held these bones since the Mesozoic era, stabilizing every crack with special glues that seep into the fossil and harden, turning fragile relics into solid, study-ready specimens. It is slow work. It is also where the giants first begin to re-emerge. When a bone is finally freed, we do not stop at the surface. We send it into the invisible world inside. High-resolution CT scanners rotate colossal vertebrae, slender claws, and even delicate skulls, building thousands of X-ray slices into a three-dimensional map. Join us as we follow those maps into digital space, where software allows researchers to reconstruct missing pieces, mirror left to right, and test how joints could swing, twist, or lock. A sauropod neck can be reassembled vertebra by vertebra on a computer screen, its range of motion explored without risking a single fracture. But bones alone do not walk. To understand how these animals really moved, we need muscles, tendons, and skin. Here, comparative anatomy steps in. We turn to living relatives and analogs. Birds with their air-filled bones and powerful hind limbs, crocodiles with sprawling strength, and large mammals that support massive bodies on column-like legs. Where do major muscle scars sit on a femur? How do hip sockets face in a creature that walks upright versus sprawling low? By matching patterns across this living menagerie, we infer where dinosaur muscles attached, how they bulked out the skeleton, and even how tails and necks were held in life. Once the digital skeleton is wrapped in virtual muscle, biomechanics can take over. Researchers build dynamic models that simulate walking, running, and even biting. How fast could a tyrannosaur accelerate before its own weight threatened to snap a leg? How much force did a ceratopsian jaw generate when shearing tough Cretaceous plants? Computer experiments estimate speeds, stresses, and energy costs, revealing whether a dinosaur was built for sprinting, long-distance roaming, or simply standing its ground as one of the biggest creatures to ever walk the Earth. Yet every reconstruction is a hypothesis, not a final truth. As new fossils emerge from other cliffs and other labs, and as scanning and modeling tools improve, earlier visions are revised. Feathers appear where scales once dominated. Postures shift from tail dragging to dynamic and balanced. Museum mounts, scientific illustrations, and the lifelike giants in documentaries set the stage for our imagination, but they remain our current best guesses, always subject to change. So what happens when we place these reconstructed bodies back into their ancient world, under Mesozoic skies and among Jurassic forests, to watch them truly live again? To watch them live again, we do not only rely on imagination, we wait for the Earth itself to speak. Sometimes that voice is quiet, a single bone weathering out of a lonely hillside. Imagine a windswept ranch in Patagonia, scrubgrass, low hills, and a worker riding the fence line. He notices something pale, curved, impossibly smooth, jutting from the rock. Not just a stone, a fragment of one of the biggest creatures to ever walk the Earth. He calls the landowner. The landowner calls the local museum. Within weeks, a small team arrives. Paleontologists, students, Technicians, standing in front of a cliff face, where enormous bones are eroding out like the ribs of a buried ship. Join us as we step back hundreds of millions of years in our minds, while they kneel in the dust and brush away grains of sediment that have not seen daylight since the Age of Giants. What they uncover first is a vertebra, a single backbone the size of a kitchen table. Then another. Then limb bones as thick as tree trunks, each one weighing hundreds of kilograms even as rock. These are titanosaur bones, like those later named Patagodon, part of a colossal sauropod that may have stretched over 35 meters from nose to tail. Day after day, they trace outlines in the cliff, jacket each fossil in plaster, and slowly realize this is not one bone or even one skeleton, but a whole graveyard of massive individuals. The logistics are as extreme as the animal. Heavy machinery crawls into the site, excavators to peel back overburden, cranes and loaders to lift plaster-wrapped bones that no group of people could safely move by hand. For weeks, sometimes months, the site becomes a temporary village. Generators buzz, tents flap in the wind. Each bone is mapped, photographed, labeled, and then hauled out along rough tracks to waiting trucks, beginning a long journey to a distant museum or university where preparation and study will continue for years. But how do we turn scattered bones into a living body? Scientists compare the limb bones and vertebrae to better-known sauropods, using scaling equations that relate bone circumference and length to body mass. They build 3D models, filling in missing parts with data from close relatives, then adjust muscle and air sac volumes to estimate realistic weights. Is this titan heavier than Argentinosaurus or slightly smaller? Does it push the upper limit of what land animals can be? Or does it reveal new room for growth in a world of scale we can barely imagine? Even with such spectacular finds, our picture is incomplete. We almost never discover complete skeletons, and the largest individuals may be the least likely to fossilize intact. Somewhere, perhaps under another quiet pasture or desert plain, the true maximum of dinosaur size still lies hidden. This means the record books are provisional, and the next fence line discovery could rewrite what we think is possible. If the biggest creatures to ever walk the earth rarely leave us complete skeletons, where else can we look for them? We look down, at the ground they once crossed, at the traces their massive bodies pressed into mud, sand, and ash. Before humans, before cities, before history itself, entire valleys recorded the daily traffic of giants, not in bones, but in footprints. Long trackways of three-toed prints march across ancient shorelines in parallel lines, some sets so tightly spaced and uniform that they almost certainly belong to herds moving together. Pace length and depth tell us how fast they walked, whether they were accelerating, even how much weight each step carried. In a few haunting sites, predator tracks converge on herds of herbivores, frozen records of hunts that played out in a world of scale we can barely imagine. These trackways are not just isolated moments. They are behavior written across landscapes. When we map them, we see pathways along ancient riverbanks, crossings of flooded plains, and the margins of vanished lakes. We can estimate hip height from footprint size, compare it to known skeletons, and use that to cross-check speed calculations. Did a sauropod plod or power walk? How closely did juveniles follow adults? The answers are stamped into stone. Yet movement is only half the story. Life begins in the nest, and dinosaurs left clues there as well. In parts of Mongolia and Argentina, entire nesting grounds stretch for hundreds of meters, with dozens or even hundreds of clutches packed together. Eggs are arranged in careful circles or layered rows, suggesting that some species returned year after year to the same breeding colonies. Shell thickness and pore structure reveal how deeply the eggs were buried, while tiny embryonic bones inside show growth stages and development. In a few remarkable cases, skeletons of adults have been found crouched over nests, arms spread as if shielding their young. Colonial nesting and possible parental care emerge not as speculation, but as patterns repeated across the Mesozoic era. Then there are the rare moments when time preserves skin. Impressions from hadrosaurs, ceratopsians, and armored dinosaurs show scales of different sizes arranged in complex mosaics, with larger shield-like scutes scattered among fine pebbly textures. Some ankylosaurs preserve the exact placement of armor plates and spikes, locked into a natural body outline. Even more transformative are mummified specimens and fossils with feather or filament impressions, especially from the Cretaceous of China, where small theropods wear downy coats or pennant-like tail fans. These finds set the stage for the transition from non-avian dinosaurs to birds that still inhabit our modern world. One of the most surprising trace fossils does not come from feet or skin, but from what passed through the gut. Coprolites, fossilized dung, can trap plant fragments, pollen, and even bone chips. Under the microscope, we see shredded conifer needles, pulverized cycads, or splintered bone from prey. This is direct evidence of diet and digestion, showing which plants were actually eaten, how well they were processed, and how predators tore apart their meals. Taken together, tracks, nests, skin, and coprolites turn dinosaurs from static skeletons into living animals with complex behaviors, textures, and ecologies. They bridge the gap between isolated bones and entire ecosystems. Join us as we follow these traces outward, from individual animals to the ancient forests, floodplains, and coastlines that sustain them, and ask, what kind of world could support such enduring, colossal dynasties? Those ancient forests, floodplains, and coastlines feel stable when we reconstruct them. For tens of millions of years they were. Herds migrated, predators hunted, seas teemed with life. And then, in a single terrible day, the entire balance shifted. 66 million years ago, in the final moments of the Cretaceous period, dinosaur ecosystems were still thriving. On land, horned giants like Triceratops browsed in dense, fern-lined undergrowth, while colossal hadrosaurs moved in groups across coastal plains. In the oceans, mosasaurs and plesiosaurs cruised above reefs of sponges and corals, and ammonites drifted through sunlit shallows. This was not a world in decline. It was a world of scale we can barely imagine reaching its peak. As we step back hundreds of millions of years in our minds and hover above that ancient Earth, we can follow one object that does not belong. Far out in space, a rocky body roughly 10 to 12 kilometers across is locked on a collision course. It is small compared with the planet, yet massive beyond comprehension, racing toward Earth at tens of kilometers per second. In the time it takes you to finish a breath, it crosses the distance from the upper atmosphere to the surface. The target is what will one day be the Yucatan Peninsula, near the modern town of Chicxulub. When rock meets rock at that speed, the laws of physics turn brutal. The asteroid does not so much land as vanish in an instant. Its energy released in a fireball that excavates a crater about 150 kilometers wide and many kilometers deep. For a moment, a patch of the planet's crust behaves like a fluid, rebounding, slumping, and collapsing in waves of molten and shattered stone. The numbers strain our intuition. The impact unleashes more energy than billions of Hiroshima bombs, a detonation so intense that in some regions it briefly outshines the sun itself. Shockwaves rip through the crust, triggering earthquakes that would register far beyond the top of any modern scale. Around the impact site, everything is simply gone. From there, the devastation races outward. Walls of water rise as tsunamis surge across the young Gulf of Mexico and into distant shorelines, scouring coasts and dragging forests back into the sea. Nearer the crater, entire stands of trees are flattened by supersonic air blasts. Rock, dust, and vaporized target material are hurled high above the atmosphere, some pieces arcing around the globe before falling back. Join us as we follow those ejecta. As they rain down, they heat the air until, in many regions, the sky itself becomes a broiler. Forests ignite almost simultaneously, continents away from the impact. Daylight dims behind towering plumes of dust and sulfur, turning noon toward twilight. In the first minutes after impact, as flames race through once lush habitats and the heavens darken, the age of the biggest creatures to ever walk the earth begins to close. But what happens when the fires die and the darkness deepens? When the last fires fade, the real catastrophe begins. The impact has passed, but its shadow spreads across the entire planet. Dust, ash, soot, and droplets of vaporized rock surge high into the atmosphere, some flung all the way into the stratosphere. There, above the cleansing reach of rain, they linger. They spread into a global veil that wraps the ancient world in a dim, dirty twilight. Not for hours, for months to years. Sunlight that once powered colossal forests and warm, shallow seas is suddenly throttled, and photosynthesis, the basic engine of almost every food chain, stalls. This was an impact winter, not just a cold day or a bad season, but a planetary blackout. As sunlight fails, surface temperatures plunge. On land, habitats that had nurtured giants adapted to warm, stable climates are thrown into freezing nights and shortened, feeble days. In the oceans, the same loss of light hammers the floating algae and photosynthetic plankton that feed everything from tiny crustaceans to massive marine reptiles. What kind of world emerges when the base of the food web is cut away almost overnight? The rocks struck by the asteroid were rich in sulfur. Vaporized in an instant, that sulfur rose as gas and aerosols, then returned as acid rain. Join us as we follow those droplets, falling back through the darkened skies. They sting leaves, needles, and the delicate tissues of young plants. They wash into rivers, lakes, and coastal seas, stressing freshwater life and corroding the shells of marine organisms that rely on calcium carbonate. Forests already weakened by fire and darkness now endure chemical assault, and many simply do not recover. With plants dying back on land and plankton collapsing at sea, herbivores are the first to starve. Duck-billed hadrosaurs, horned ceratopsians, long-necked titanosaurs, specialized feeders that once thrived in a world of scale we can barely imagine, suddenly find empty floodplains and barren understories. Their numbers crash, and when the plant eaters fall, the great predators follow. Tyrannosaurus, giant abelisaurs, and other apex hunters, exquisitely tuned to tracking and killing large prey, face a landscape where those prey are vanishing. In an era of scarcity, being massive and specialized becomes a deadly disadvantage. Yet the asteroid did not strike a perfectly healthy Earth. For hundreds of thousands of years beforehand, immense volcanic eruptions in the Deccan Traps of India had been releasing carbon dioxide, sulfur, and ash. These eruptions warmed some regions, cooled others, and may have already stressed ecosystems with shifting climates and intermittent acid rain. The impact did not start the crisis so much as it may have set the stage for a rapid, irreversible collapse. Still, not everything died. Many small animals survived, especially those that could burrow, shelter in water, or endure long periods with little food. Creatures that ate seeds, detritus, insects, or almost anything they could find had a crucial advantage over the giants. Among them were small, feathered theropods, the only dinosaurs to make it through. In the next section, we will follow these avian survivors as they inherit a transformed Earth and begin a new chapter in dinosaur evolution. Those fragile feathered survivors step into a world of ash and silence. The age of the giants has ended, but the age of dinosaurs has not, because every bird you see today is, in a strict evolutionary sense, a dinosaur. This is the first crucial idea. The line that leads from small Cretaceous theropods to modern birds is unbroken. They are avian theropods, the only branch of the dinosaur family tree to cross the fire break of the end Cretaceous extinction. When we watch a flock of starlings twist over a field, or a hawk circling high above a city, we are watching the last living echoes of the biggest creatures to ever walk the earth. Why did they make it when titans like Tyrannosaurus did not? To answer that, we need to shift our sense of scale, not toward the colossal, but toward the small. Most surviving birds at the KPG boundary were tiny by dinosaur standards, often no heavier than a modern crow or pigeon. Small bodies need less food, less territory, and can reproduce more quickly. In a world where global food chains had just collapsed, that difference was not subtle. It was life or death. Many of these birds could fly, or at least glide and move nimbly between habitats. Wings were not just tools for soaring over a lush Cretaceous forest. They became lifelines, allowing survivors to escape local wildfires, reach distant patches of shelter, or track the last pockets of usable resources. Even flightless lineages that endured likely shared this mobility in another form. Quick legs, flexible behavior, and an ability to exploit the edges of shattered ecosystems. Diet may have been the decisive advantage. While specialized predators and gigantic herbivores depended on a constant flow of fresh meat or vegetation, many early birds were generalists. They could eat insects, small invertebrates, and, critically, seeds. Seeds are nature's time capsules. Buried in soil or locked inside cones and fruits, they can endure dark, cold conditions for months or even years. When sunlight was choked off and photosynthesis stalled, fresh leaves vanished, but seed banks persisted. Granivorous birds, pecking in the dust for these hard little packages of stored energy, tapped into a food source that large plant eaters and apex carnivores simply could not use. Now place that beside an animal like T-Rex. A single adult required vast territories stocked with multi-ton herbivores, which in turn needed endless fields of foliage. Remove the plants, and the herbivores crash. Remove the herbivores, and the predators follow. The very traits that made these animals magnificent in a stable Cretaceous world, massive size, powerful jaws, highly specialized feeding, set the stage for their downfall when that world unraveled. Yet we should be cautious. Was survival only about size, wings, and seeds? Geography and chance almost certainly played their parts. Populations far from the impact site, or sheltered in certain latitudes and ecosystems, may have had slightly better odds. Some bird lineages still vanished, others clung on by the thinnest margin. Join us as we follow those fragile lineages into the Paleogene, where they diversify, spread, and over tens of millions of years, reclaim the skies of a world reborn. As birds begin to reclaim the skies of a world reborn, something else is stirring below. In the shadows of this new Paleogene Earth, a different kind of dynasty is quietly preparing to rise. Throughout the Mesozoic era, mammals were present, but they did not rule. For more than 100 million years, they lived mostly in the margins, small, often nocturnal, and forced into ecological corners by the dominance of dinosaurs. Before humans, before cities, before history itself, they survived as insect eaters, burrowers, and climbers under the feet of giants. Yet they were already surprisingly diverse in form, from shrew-like insectivores to gliding species and robust, badger-like diggers. The age of dinosaurs constrained them, but it also quietly set the stage for what came next. When the asteroid struck and the non-avian dinosaurs vanished, those constraints collapsed almost overnight on geological timescales. Entire ecological roles suddenly stood empty. Large herbivores that had once been hadrosaurs and ceratopsians were gone. Apex predators like tyrannosaurs no longer stalked the floodplains. Arboreal specialists, mid-sized omnivores, fast-running grazers and browsers. Across continents, these niches were vacant. In the silence after the extinction, mammals began to expand, experiment, and radiate into that open ecological space. In the early Paleogene period, we see the first waves of this mammalian radiation. Join us as we step back hundreds of millions of years in concept, then move forward into this transformed world where strange, often massive mammals take over roles once filled by dinosaurs. In North America and Eurasia, hoofed herbivores evolved into forms that would later give rise to horses, deer, and rhinos, while creodonts and early carnivorans emerged as formidable predators. In South America, isolated by shifting continents, bizarre lineages of native ungulates and terror birds created ecosystems unlike anything alive today. In Africa and India, early relatives of elephants, hyraxes, and primates shared forests and river valleys, building a new tapestry of life out of ancient threads. Some mammals grew large, very large. Oligocene rhino relatives like Paraceratherium likely rivaled or exceeded the mass of a modern elephant, and giant ground sloths later pushed terrestrial size even further. But no land mammal has ever reached the colossal bulk of the biggest creatures to ever walk the earth, the giant sauropod dinosaurs. Why not? The combination of dinosaur physiology, bird-like lungs, air-filled bones, and the warm, high CO2 conditions of the Mesozoic appears to have been uniquely suited to extreme gigantism, creating a world of scale we can barely imagine and have never seen repeated. For us, this transition is not just an abstract shift in fossil faunas. It is the opening chapter of our own story. Without the dinosaur extinction, would primates have remained small, nocturnal insect eaters in the understory? Would apes, and eventually humans, ever have emerged from the canopy to reshape the planet? The rise of mammals after the extinction did more than refill empty niches. It ultimately produced a species capable of asking these questions. Yet even as mammals spread across the continents, another group of dinosaur descendants was also evolving, diversifying, and learning to master more than just the air. To see how their story intertwines with ours, we have to follow the birds beyond flight. Those birds we followed out of the Cretaceous did not vanish into the sky and leave our world behind. They came back down into forests, fields, and cities, and quietly turned the Age of Dinosaurs into something that still surrounds us. We do not just study dinosaurs as fossils in distant deserts. We live inside the landscape they left. Across much of the planet, the rocks beneath our feet were laid down during this colossal era. In many regions, the right layers of Triassic, Jurassic, or Cretaceous age lie just a few meters below farms, suburbs, and highways. Under a wheat field in Argentina, there might be the neck vertebrae of a sauropod longer than a bus. Beneath a housing development in Montana, the ribcage of a hadrosaur could be locked in stone. Right now, there are probably undiscovered skeletons resting under parking lots, schoolyards, and backyards, waiting for erosion, construction, or a curious observer to reveal them. When we say we step back hundreds of millions of years, we are often only stepping down a few meters in the rock. Road cuts, riverbanks, and quarries slice through time, exposing the muds, sands, and volcanic ashes that once buried the biggest creatures to ever walk the earth. A child picking up a strange bone on a hillside may be the first human to touch that animal since it died in the Mesozoic. The deep past is not far away. It is just mostly hidden. And above those rocks, the dinosaurs are still here. Every pigeon on a city street, every sparrow at a feeder, every heron stalking through a wetland is a living dinosaur, carrying Mesozoic adaptations into the modern world. Hollow, air-filled bones, a high-performance respiratory system, feathers that began as insulation or display, now refined into wings that can cross oceans. When a crow watches you with a sharp, sideways glance, you are seeing the legacy of ancient theropod hunters, compressed into a smaller, quicker body. This living connection and the fossils beneath us have set the stage for entire human industries. Museums build colossal halls around mounted skeletons of Tyrannosaurus, Triceratops, and Argentinosaurus, drawing millions of visitors who come to stand beneath bones that once shook the earth. National parks and protected badlands preserve famous bone beds, where tourism, research, and education intertwine. Field crews camp for months to uncover a single articulated skeleton. Nearby, families walk interpretive trails that explain how those rocks formed and how life responded to climate shifts, sea level changes, and mass extinction. Beyond science and economics, dinosaurs dominate our imagination. They stride through films, novels, paintings, and children's toys, acting as ambassadors to deep time. For many of us, a childhood fascination with these giants is the first doorway into geology, evolution, and the vast history of our planet. They make abstract numbers real. They turn 165 million years into teeth, footprints, and feathers. In this way, the Age of Dinosaurs is not just an ancient chapter that ended at Chicxulub. It is woven into our landscapes, our ecosystems, and our stories. To see how we uncovered that story in the first place, we now turn to the people, tools, and discoveries that built the science of paleontology itself. When we step back hundreds of millions of years, the Age of Dinosaurs becomes more than a parade of spectacular skeletons. It becomes a record of how far a living planet can be stretched and where its limits begin to break. Across the Mesozoic era, Earth itself kept changing the rules. Continents that were once fused into the supercontinent Pangaea slowly tore apart, opening new oceans and reshaping coastlines. Yet dinosaurs adapted. They spread from arid interior basins to humid coastal plains, from equatorial floodplains to polar forests where months of winter darkness cloaked the land. Fossils of hadrosaurs and small feathered relatives near the poles show that even in chill seasonal climates, these giants and their kin could endure long nights and cooler temperatures. This adaptability was forged in crisis. Dinosaurs emerged in the shadow of the Permian-Triassic extinction, when most species on Earth vanished and ecosystems were stripped to their foundations. They survived the Triassic-Jurassic event, when intense volcanism and climate upheaval swept away many competitors. Later, regional droughts, shifting monsoons, and rising seas repeatedly fractured habitats. Each time, some lineages radiated and others disappeared, reminding us that resilience and vulnerability are intertwined. Life can recover, but it does not always recover in the same form. Their bodies also trace the physical boundaries of what is possible. Sauropods like Argentinosaurus and Patagotitan pushed land animal size toward an upper limit, with masses rivaling a small herd of elephants in a single body. Air-filled bones, efficient lungs, and long necks that could sweep across entire groves set the stage for a world of scale we can barely imagine. Yet even these colossal herbivores were constrained by how much plant matter landscapes could produce, how quickly they could grow, and how their hearts pumped blood to elevated heads. There is a ceiling on body size, metabolism, and population density, and dinosaurs press right up against it. When we read their story alongside ours, a pattern emerges. In the Mesozoic, carbon dioxide levels rose and fell, sea levels flooded continents, and climates warmed and cooled. Some changes unfolded slowly enough for evolution to keep pace. Others, like the sudden shock at the end of the Cretaceous, were simply too rapid and too intense. The causes may differ from today's human-driven warming, but the lesson is similar. The biosphere is exquisitely sensitive to speed. So what do the biggest creatures to ever walk the Earth really teach us? That our planet is both generous and fragile. That it can host forests at the poles and giants on the plains, yet still reach tipping points where entire worlds of organisms vanish. Join us as we carry these lessons forward into the next section, where we explore how modern science, technology, and imagination work together to reconstruct this ancient world in ever finer detail. If the rocks and bones of the Mesozoic let us glimpse the past, modern technology lets us walk right up to it and turn on the lights. We are no longer limited to chisels and hand lenses. Today, we can peer inside the very atoms of this ancient world. Join us as we follow a fossil beyond the dig site and into the lab. Here, advanced imaging techniques such as synchrotron scanning and high-resolution CT take over. These machines fire intense beams through dinosaur bones, building three-dimensional images slice by microscopic slice. What looks like a simple rib on the outside can reveal growth rings like those in a tree trunk, delicate blood vessel canals, even the ghostly outlines of soft tissues and feathers pressed into stone. Suddenly, a bone is no longer just a relic. It becomes a record of how a giant actually grew, healed, and moved. From structure, we move to chemistry. Geochemical tools allow us to read the signatures of temperature, diet, and migration locked inside dinosaur teeth and bones. Ratios of oxygen isotopes can suggest whether a sauropod grew up in cooler highlands or warm lowlands. Carbon and nitrogen patterns hint at whether a predator specialized in hunting juveniles or tackled the biggest creatures to ever walk the earth. In some fossils, strontium isotopes even trace yearly journeys, revealing herds that may have marched across entire continents in search of seasonal rains. Once we know what a dinosaur was made of and where it lived, we can ask a deeper question. How did it actually function? Computer simulations and robotics now set the stage for a new kind of experiment. Digital skeletons are wrapped in virtual muscles, then tested to see how fast a theropod could run before its legs snapped, or how a hadrosaur's tail balanced its body. Robotic models of jaws crush bone and plant material to measure bite forces and feeding mechanics. Even the famous sauropod neck becomes a test bed, as engineers and paleontologists collaborate to see how far it could really sweep, how high it could reach, and whether those colossal arcs were held upright or mostly horizontal. All of this unfolds while new fossil sites continue to transform the map. Vast regions of Africa, interior Asia, and even ancient polar coastlines remain barely explored. Every season, teams uncover bones that hint at species rivaling Argentinosaurus or Patagotitan in size, or lineages that blur the boundaries between known groups. How many more giants lie under desert dunes, rainforest soils, or Antarctic ice? We have studied dinosaurs seriously for only about 2 centuries, yet we are dissecting a 165 million year saga. Our image of the age of dinosaurs is not fixed. It is evolving as quickly as our tools. As we step back hundreds of millions of years with sharper eyes and stronger machines, we must ask, what if the most radical discoveries, the ones that rewrite everything we think we know about this era, are still buried, waiting for the next scan, the next drill core, the next shovel of Earth? So now, before we close this million-year saga, we invite you to take one more journey. Not with rockets or time machines, but with your own imagination. Start where we stand today in the modern world of cities, satellites, and smartphones. Then, in your mind, begin to rewind. Oceans drain back from the coasts. Ice sheets retreat. Forests shift and vanish. Human history collapses into a thin, fragile film on the surface of the Earth. Keep going. Past the first cities, past the first farms, past the first humans. In a heartbeat of geological time, our entire story disappears. Now, let the clock run backward a little farther until you reach a night sky lit not by street lamps, but by a falling star. The Chicxulub asteroid plunges upward from the Yucatan. The shockwave unhappens, the wildfires unburn, and the last non-avian dinosaurs stand once more on the Cretaceous plains. For a moment, the extinction rewinds, and the age of giants breathes again. Join us as we strip away the impact winter and step into that late Cretaceous world. You see T-Rex stalking along a humid coastal floodplain, each footfall sending a dull tremor through the mud. Hadrosaurs move in wary herds, and horned dinosaurs lock frills and horns in slow, powerful contests. Above them, feathered raptors glide between conifer trunks, their wings catching shafts of green light as flowering plants carpet the understory. This is a world of scale we can barely imagine, yet it was once utterly real. Now rewind deeper, past the Cretaceous into the Jurassic period. Continents slide back together. Shallow seas drain from the interiors of landmasses. You stand in a valley ringed by volcanic hills as colossal sauropod herds move like living hillsides across the horizon. Their necks sweep through the canopy, stripping foliage from tree ferns and conifers, their air-filled bones and bird-like lungs allowing them to grow into some of the biggest creatures to ever walk the earth. Each step shakes the ground. Each breath moves a volume of air larger than a room. Keep turning the clock, all the way to the Triassic. The forests thin into open, sun-blasted deserts. Here, tiny early dinosaurs dart between the legs of dominant archosaurs, quick, light, and easily overlooked. Chelephysis-like hunters weave through scrub, while larger, lumbering reptiles still rule the rivers and plains. Who, looking at these small, agile forms, would guess they were the seeds of a future empire of giants? Across these 165 million years, entire lineages rise, diversify, and vanish, long before our own species appears. The Mesozoic era is not a single frozen scene. It is an ancient library of worlds, each period turning a new page. Earth has been many different planets in its deep past, from Triassic deserts to Jurassic fern forests to Cretaceous flower-rich coasts. And the Age of Dinosaurs is only one long chapter in a far greater book. As we return in our minds to the present, we carry that chapter with us. What does it mean to live on a planet whose surface can be rewritten so completely? How should we think about our own brief moment, knowing how many worlds came and went before us? In our final recap, we will gather these questions and set the stage for how you can stay curious, stay engaged, and help uncover whatever stories still lie buried beneath our feet. In this final sweep across deep time, we can now see the Age of Dinosaurs not as scattered bones, but as a single, continuous story. A story that begins in ruin, climbs to unimaginable heights of size and diversity, and ends in a flash of fire from the sky. After the Permian extinction nearly erased complex life, the Triassic opened as a world of survivors and experiments. Small, agile reptiles tested new body plans, and among them, the first true dinosaurs appeared, lightweight, fast, and opportunistic. On the supercontinent Pangaea, with climates swinging between searing heat and seasonal drought, these early forms learned to endure scarcity and stress. That harsh beginning set the stage for everything that followed. When we step back hundreds of millions of years into the Jurassic, the picture transforms. Pangaea began to rift apart. Climates grew more humid and stable, and vast forests of conifers, cycads, and giant ferns spread across the continents. In that green engine room, sauropods seized their chance. Air-filled bones, powerful hearts, and bird-like lungs allowed them to push body size to extremes. Creatures such as Argentinosaurus and its colossal kin, longer than jet airliners and weighing more than a convoy of trucks, became the biggest creatures to ever walk the earth. The environment did not merely host these giants, it built them. High atmospheric CO2, warm temperatures, and lush year-round vegetation fed massive herbivores, which in turn supported equally impressive predators. As the Cretaceous period unfolded, continents drifted farther apart, shallow seas flooded interiors, and flowering plants rewired ecosystems. In this shifting world, an evolutionary arms race intensified. Ankylosaurs turned their bodies into living tanks. Triceratops wielded horns and frills like shields and spears. Apex hunters such as Tyrannosaurus rex developed bone-crushing bites and keen senses, specialized for tracking and toppling prey in a world of scale we can barely imagine. Yet even this long supremacy proved fragile. At the KPG boundary, an asteroid impact and massive volcanism combined to darken skies, chill the climate, and collapse food chains. For most non-avian dinosaurs, 165 million years of success ended in a geological instant, but not all of them vanished. Small, feathered, warm-blooded lineages had already taken to the trees and the air. We call them birds. Every sparrow, eagle, and penguin is a living dinosaur, carrying forward lungs, feathers, and behaviors first refined in that ancient era. What do we learn from tracing this rise and fall? We see that life responds to planetary change with invention, new anatomies, new ecologies, new giants. We also see that no dominance is permanent. As we move to our closing thoughts, join us as we turn this deep time perspective back on ourselves and ask what it means to be the latest experiment on a restless planet. We have spent this journey tracing an ancient world of scale we can barely imagine, from tiny Triassic survivors to the biggest creatures to ever walk the Earth. Now for a moment, the story turns to you. If you had a single day in deep time, where would you go? Would you step back hundreds of millions of years into the harsh Triassic to watch the first true dinosaurs pick their way across floodplains still scarred by extinction? Would you choose the Jurassic, the golden age of sauropod giants, and stand beneath a forest canopy of conifers and giant ferns as a herd of colossal longnecks passes like living towers? Or would you travel to the Cretaceous to see flowering plants spreading, armored and horned dinosaurs clashing, and predators like Tyrannosaurus testing the limits of power? Tell us in the comments which period you would visit and why. Among all the species we have met, which dinosaur stayed with you the most? Perhaps a high-browsing Brachiosaurus, head lost in the canopy. Perhaps a feathered predator, reminding us how close birds stand to their ancient cousins. Perhaps a titan like Argentinosaurus, known from only a handful of massive bones, yet still redefining what a land animal can be. Share your favorite in the comments, and tell us whether you think we have already uncovered the largest species, or if even greater giants still lie buried beneath fields, deserts, and city streets. Our exploration of this era does not end here. When you like this video or subscribe, you are not just supporting a single documentary. You are joining an ongoing exploration of deep time. Join us as we follow future trails into specific dinosaurs, individual formations, and remarkable fossil discoveries that set the stage for new insights into dinosaur evolution, behavior, and extinction. Each new bone, each new site, lets us refine this grand narrative. There are simple ways to continue this journey beyond the screen. You can visit a local natural history museum and stand in front of real fossil skeletons, tracing with your eyes the same vertebrae and limb bones we have discussed. You can look up a geological map and discover whether rocks from the Triassic, Jurassic, or Cretaceous lie near your home, imagining the ecosystems that once covered that ground. Or you can simply watch the birds outside your window, aware that you are observing living dinosaurs, survivors of the last great mass extinction. The age of dinosaurs is over, but the story of life on Earth is not. Our own species has appeared only in the last instant of this 165 million year saga, yet our actions now shape climates, oceans, and habitats on a planetary scale. When we step back to see giants rise and fall, continents drift, and ecosystems transform, we gain perspective on our brief chapter. Understanding this deep past is not an escape from the present. It is a guide. By learning how life has endured upheaval before, we can help write a future in which the legacy of this ancient world is not only remembered in stone, but honored in the living planet we share. So before we leave this ancient world behind, imagine this. You are not just observing from a distance. You are there, For one day, stripped of modern weapons, wrapped only in basic protective gear, you step back hundreds of millions of years and wake up in the age of dinosaurs. The challenge is simple in words, but immense in reality. Could you survive 24 hours? We will set the stage with 3 doors. Behind the first is the Triassic, just after the greatest mass extinction in Earth's history. The air is hot, often dry, with wild swings between drought and sudden floods. Dinosaurs are still small and lightly built, like Colossal, and the biggest creatures to ever walk the Earth have not yet appeared. That sounds safer, but the risks are subtle. You face a harsh climate, little shelter, and ecosystems still unstable from catastrophe. Croc relatives and other reptiles share the role of top predator, and you are a strange, slow primate in a landscape that does not know you. Behind the second door is the Jurassic, the golden age of the giants. Here, colossal sauropods like Brachiosaurus and Diplodocus reshape forests into open parklands. Their sheer size might be your shield. A human is beneath their notice. Yet where there are herds of massive herbivores, there are also large theropods, stalking the edges like living scythes. The climate is warm and generally more humid, with lush vegetation, but also fewer safe hiding places in open floodplains. One wrong move near a waterhole, and you are simply another confusing shape in a predator's field of view. The third door opens onto the Cretaceous, a world of scale we can barely imagine in its complexity. Flowering plants spread across continents, insects diversify, and regional dinosaur faunas evolve as landmasses drift apart. This is the age of Tyrannosaurus, of horned giants like Triceratops, of armor-plated titanosaurs. Ecosystems are dense, noisy, and crowded. That density offers more cover, more potential hiding spots, more microhabitats to vanish into. It also means advanced predators with keen senses, parasites and biting insects, and unfamiliar pollens and spores that your immune system has never encountered. And in every period, the dinosaurs are only part of the danger. The atmosphere holds different greenhouse gas levels. Even the air may feel heavier, warmer, or strangely scented. Insects probe your skin, some carrying ancient diseases. Plants that look inviting could be toxic, spined, or dripping resins that glue your gear in place. A simple cut, in a world with no medicine and unfamiliar microbes, could be as deadly as any theropod. So which door would you choose? And what would your survival strategy be? Would you cling to rocky Triassic high ground, shadow Jurassic herds for protection, or vanish into a Cretaceous forest and hope the giants pass you by? Join us as we turn this into a shared experiment. Tell us in the comments your chosen period, your hiding places, and your plan for making it through the night. Because in the end, this thought experiment is humbling. It reminds us that we are exquisitely adapted to our own time, and that these vanished eras were not built for us. Yet there is one more twist to this story of survival, and it involves the only dinosaurs that never left. Those survivors are our bridge. They link our fragile human moment to a world of scale we can barely imagine, and to the people who have spent their lives uncovering it. As the camera slows and we step back hundreds of millions of years in our minds, the credits of this story are not just names on a screen. They are generations of paleontologists hiking into burning deserts and frozen badlands, field crews hauling plaster jackets that weigh as much as refrigerators, preparators in quiet labs freeing ancient bone from stone, and local communities who share their land, their stories, and their knowledge of where the fossils sleep. Before we ever meet the biggest creatures to ever walk the earth in a museum hall, they pass through countless human hands. In Patagonia, ranchers and road workers first notice strange shapes eroding from hillsides, setting the stage for colossal titans like Argentinosaurus and Patagotitan to emerge from the rock. In the American West, the layered cliffs of the Morrison Formation hold the intertwined skeletons of Diplodocus, Camarasaurus, and Allosaurus, revealed by teams who return season after season, year after year. Follow the montage now as we cross continents. Over Mongolia's Gobi Desert, sunset light rakes across dunes where Velociraptor and Protoceratops once struggled in sandstorms, and where local herders and scientists together have transformed scattered bones into a detailed ecosystem. In China's Liaoning province, farmers turning their fields uncover wafer-thin slabs preserving feathers, skin, and soft tissues, giving us the first clear view of how birds rose from their dinosaur ancestors. Behind every fossil mount, there are institutions that refuse to think in short time frames. Museums curate collections that will outlive all of us, preserving fragile specimens so that future scientists with better tools can ask new questions. Universities train the next generation of researchers, artists, and technicians who will carry this work into the next century. Public funding bodies quietly sustain projects that may take decades from the first shovel in the ground to the final publication. When you walk under a massive sauropod skeleton or stare into the teeth of a T-Rex, you are seeing the result of this long chain of effort. From the first permit signed to the last data point entered, it is a collaborative achievement that spans nations, languages, and cultures. Join us as we recognize that no single person discovers a dinosaur. Entire communities do. So where do you fit into this story? If these ancient giants move you, you can turn that feeling into real impact. Visit your local museum, support science education in your schools, and back the institutions in your region that protect fossils and landscapes. Somewhere just beneath the surface, the next chapter of this era is waiting to be found, and all of us help decide whether it will ever see the light. But before we leave this era behind, we return to where it ended. Not in fire, not in impact, in evening light. Step back hundreds of millions of years with us to a late Cretaceous floodplain at dusk. The heat of the day is bleeding away, and the sky is a deep band of orange and violet over the silhouettes of giants. On the horizon, a herd of massive herbivores moves in slow procession, necks rising like living cranes against the sinking sun, their shadows stretching across river mud that still holds the day's footprints. They are the biggest creatures to ever walk the earth, yet in this moment, they are quiet shapes, not statistics. A young sauropod pauses at the water's edge, ribs faintly visible as it takes in one last drink. Farther off, dome-headed and horned dinosaurs graze among low cycads and the first flowering shrubs, pulling at leaves that have no idea this is one of their final evenings in a world of scale we can barely imagine. Above them, the air is busy. Pterosaurs glide on slow, economical wing beats, riding the last thermals of the day. One banks across the face of the sun, just a dark, angular outline, then vanishes into shadow as the light drops. The calls of distant carnivores drift over the plain, not as roars, but as low, echoing notes that roll along the ground like distant thunder. As we watch, the color drains gently from the sky. The blazing horizon softens to embers. The first stars appear so gradually that at first, you do not notice. A pale point here, another there, pricking through the deepening blue above the fading afterglow. Night is arriving the way it always has, but now if we look closely, we can sense that something else is moving through that darkness, far beyond their sight. How many evenings like this passed, utterly unobserved by human eyes? For 165 million years, sunsets washed over Triassic survivors, Jurassic sauropod strongholds, and Cretaceous arms races of horn and armor. And not once did a human see the colors or hear the sounds. These scenes rose and faded again and again, written only in light and wind and memoryless sand. And yet, through fossils, physics, and imagination, we can stand here now. Join us as we use bones, trackways, and ancient sediments to set the stage for this final quiet, reconstructing the angle of a neck, the span of a wing, the plants that perfumed the air. Through science, art, and shared curiosity, We give this lost world a second audience. Listen as the last calls of these dinosaurs echo and thin, their voices blurring at the edges. A low bellow becomes the rumble of distant traffic. A sharp, bird-like cry resolves into a modern sparrow on a city rooftop. The Cretaceous night dissolves into our own, and the continuity of life carries us from their extinction into our present Earth, where the story of these ancient giants is finally being heard. That continuity does not end with the last dinosaur. It runs straight through the rock, through the fossils, through the science, and into you. 165 million years can feel so vast that it becomes almost abstract, a blur of names, dates, and vanished landscapes. Yet your own timeline begins in a single, precise moment. Now, with what you choose to learn, to notice, and to do next. Before humans, before cities, before history itself, the Earth belonged to giants. Not just big animals, but the biggest creatures to ever walk the Earth, living in a world of scale we can barely imagine. Now the planet that once carried sauropods longer than airplanes and tyrannosaurs with bone-crushing bites carries us instead. That is not a separate story. It is the same story, unfolding in a new chapter, in the same ancient world under the same sky. When we step back hundreds of millions of years, we gain perspective on our own brief era. We see how extinction reshaped life, how evolution experimented with feathers, armor, and colossal size, how climate and continents set the stage for every ecosystem that followed. Understanding that deep time is not about memorizing every period. It is about realizing that the ground beneath your feet holds the memory of oceans, forests, deserts, and impacts powerful enough to reset life itself. So, where does your part begin? It can start with a single question you decide to chase, a nearby rock outcrop you look at differently, a fossil in a museum you pause to really see. Join us as we move from this wide overview into focused journeys. Deep dives into titans like Argentinosaurus and T-Rex, episodes exploring the skies of the pterosaurs and the seas of the marine reptiles, and guides on how to read the rocks and fossils near where you live. If this exploration of the Age of Dinosaurs has stirred your curiosity, help it travel further. Like this video, subscribe to the channel, and share it with someone who loved dinosaurs as a child, or who still feels that pull toward the ancient Earth today. Each new viewer is another mind stepping into deep time, another voice added to a growing conversation about our planet's past. Use the comments below as an open field site rather than a closed book. What questions do you still carry about dinosaurs, about mass extinctions, about how we know what we know? What moments from this journey do you want to see expanded into their own expeditions? Your questions can shape what we uncover next. The Age of Dinosaurs is over, but the age of understanding them is still young. The same Earth that once echoed with sauropod footsteps and tyrannosaur roars now echoes with our choices. By learning how this planet has changed, survived, and renewed itself, we take the first step toward caring for its future. Stay curious. Your timeline starts now.